Imagine standing beneath the night sky, gazing upward at thousands of glittering stars scattered across the darkness like diamonds thrown against black velvet. Your eyes sweep across constellations your ancestors named millennia ago, patterns that guided sailors across uncharted oceans and inspired poets to write verses about infinity. Among those countless points of light, one star holds a secret that humanity has only recently begun to uncover, a secret that challenges everything we thought we knew about our place in the cosmos. That star is invisible to your naked eye, hidden in the southern constellation Centaurus, yet it stands closer to our world than any other star in the universe. Its name is Proxima Centauri, and though it dwells right next door in cosmic terms, separated from us by a gap so vast that light itself takes more than 4 years to cross it, this tiny red ember burns with mysteries that could reshape our understanding of size, distance, and what it means to be small in an incomprehensibly large universe. This is not just a story about measuring a star. This is a journey into the heart of how we perceive reality itself, how we learn to reach across the void with nothing but mathematics and ingenuity to grasp truths about worlds we may never touch, and how one seemingly insignificant speck of light became the gateway to humanity's greatest dreams of reaching beyond Earth to touch another sun. Introduction to our cosmic neighborhood. The universe stretches before us in scales that defy human comprehension, expanding across distances so enormous that our everyday measurements become meaningless. When we talk about the size of stars, we are not simply discussing objects that are bigger than Earth or bigger than mountains. We are confronting entities so vast that our planet could be swallowed whole without leaving a trace, consumed like a grain of sand dropping into an ocean. Yet within this hierarchy of cosmic giants, Proxima Centauri occupies a peculiar position, one that forces us to reconsider what we mean when we ask how big something really is. Size in space is not merely about width or volume. It encompasses mass, brightness, gravitational influence, and the fundamental processes that allow a ball of gas to shine for billions of years. Proxima Centauri challenges our assumptions because it represents the smallest type of star capable of sustaining nuclear fusion, the cosmic fire that transforms hydrogen into helium and releases the energy that makes stars shine. To understand how big Proxima Centauri really is, we must first understand where it sits in the grand catalog of stellar objects, and we must recognize that our sun, that brilliant yellow disk we see every day, is actually quite large compared to the majority of stars in our galaxy. Our journey begins not in the distant past, but in the present moment, in a time when humanity has developed the tools to measure the unmeasurable and comprehend the incomprehensible. We live in an era where spacecraft have left our solar system, where telescopes peer billions of light years into space, and where computers simulate the birth and death of entire galaxies. Yet for all this technological sophistication, the simple question of how big our nearest stellar neighbor truly is remains surprisingly complex. Proxima Centauri does not reveal its secrets easily. It hides behind layers of physics that took centuries to unravel, concealed by distances that make direct measurement impossible and shrouded in the peculiar properties of red dwarf stars that behave unlike any other class of stellar objects. This documentary script will take you through every aspect of this question, from the ancient observations that first cataloged the star to the cutting-edge research that continues to refine our understanding today. We will explore not just the numbers but the meaning behind them, not just the facts but the implications for life, for exploration, and for humanity's future among the stars. The discovery of our nearest neighbor. The story of Proxima Centauri begins not with its discovery, but with humanity's gradual awakening to the true nature of stars. For thousands of years, people looked at the night sky and saw points of light fixed to a celestial sphere, perfect and unchanging, divine and untouchable. The ancient Greeks developed intricate models of nested crystal spheres carrying stars around Earth, while Chinese astronomers meticulously recorded the positions of celestial objects for astrological divination. No one imagined that stars were other suns, burning at distances so great that their light took years to reach our eyes. The conceptual leap required to understand stars as distant suns came slowly, fought against by philosophical and religious traditions that placed Earth and humanity at the center of creation. It was not until the 16th and 17th centuries, when Copernicus, Galileo, and Kepler dismantled the geocentric model of the universe, that astronomers began seriously considering that stars might be suns scattered through infinite space. This realization immediately raised a profound question. If stars are other suns, how far away must they be to appear so dim? The quest to measure stellar distances consumed astronomers throughout the 18th and 19th centuries. The method they sought was parallax, the apparent shift in a star's position when viewed from different points in Earth's orbit around the Sunday. Imagine holding your finger at arm's length and closing first one eye, then the other. Your finger appears to jump against the background. This same principle applies to stars, but the effect is so tiny that it requires extraordinarily precise instruments to detect. Year after year, astronomers attempted to measure stellar parallax and failed, frustrated by the limitations of their telescopes and the interference of Earth's atmosphere. The stars seemed impossibly distant, their parallax shifts too small to detect. Then in 1838, a German astronomer named Friedrich Bessel succeeded in measuring the parallax of a star called 61 Cygni, proving that stars were indeed other suns at vast distances. This breakthrough opened the door to mapping the three-dimensional structure of our cosmic neighborhood. But it would be many decades before astronomers turned their attention to the relatively faint stars of the southern sky where Proxima Centauri hides. The Alpha Centauri system, a bright pairing of stars visible to the naked eye in the southern constellation Centaurus, had long fascinated astronomers because of its proximity. In 1839, just a year after Bessel's parallax measurement, Thomas Henderson measured the distance to Alpha Centauri and found it to be the closest star system to our Sunday. But Alpha Centauri is actually a binary system, two stars orbiting each other, both considerably larger and brighter than our Sunday. For decades, astronomers studied this system intensively, mapping the orbital dance of the two bright stars and searching for any planets or companions. It was not until 1915 that a Scottish astronomer named Robert Innes, working at the Union Observatory in Johannesburg, South Africa, noticed something unusual while examining photographic plates of the Alpha Centauri region. He found a faint red star whose motion across the sky matched that of the Alpha Centauri binary pair, suggesting it was part of the same system despite being separated by a considerable distance. Innes named this new discovery Proxima Centauri because measurements suggested it might be slightly closer to Earth than the binary pair, making it the closest known star to our solar system. The discovery of Proxima Centauri did not make headlines or capture public imagination the way discoveries of planets or comets often did. This tiny red star was far too dim to see without a telescope, and its properties seemed unremarkable to astronomers accustomed to studying brilliant giants and exotic stellar phenomena. Proxima Centauri represented the most common type of star in the galaxy, a red dwarf, but red dwarfs were poorly understood in the early 20th century. These stars were so faint and cool that they challenged the theoretical models of stellar structure then being developed. Scientists knew that stars generated energy through some internal process, but the discovery of nuclear fusion as the power source for stars still lay decades in the future. Without understanding how stars worked, astronomers could not accurately determine the size, mass, or age of objects like Proxima Centauri. The star remained a footnote in astronomical catalogs, its significance appreciated only by a handful of specialists who recognized that our nearest stellar neighbor might hold clues to understanding the most abundant type of star in the universe. As the 20th century progressed, technological advances in spectroscopy and photometry allowed astronomers to study Proxima Centauri in greater detail. Spectroscopy, the technique of splitting starlight into its component colors and analyzing the patterns of bright and dark lines, revealed the chemical composition and surface temperature of stars. Photometry, the precise measurement of stellar brightness, helped astronomers understand how much energy stars emitted. When these techniques were applied to Proxima Centauri, they confirmed that it was indeed a red dwarf, a star with a surface temperature of only about 3,000 degrees Celsius, barely half the temperature of the Sun's surface. Its spectrum showed strong absorption lines from molecules like titanium oxide, which can only exist in relatively cool stellar atmospheres. The star's brightness was incredibly faint, roughly 1/600th the luminosity of our Sun, meaning it emitted far less energy despite being relatively close. These observations painted a picture of a star that was small, cool, and dim, but they could not yet determine its exact size without understanding the physics of stellar structure. Understanding red dwarf stars. To truly comprehend how big Proxima Centauri is, we must first understand what makes red dwarf stars different from larger stars, like our Sunday stars, are not solid objects like planets or asteroids. They are massive balls of plasma, gas heated to such extreme temperatures that electrons are stripped from atoms, creating a soup of charged particles held together by gravity. The balance between gravitational collapse and outward pressure from nuclear fusion reactions determines a star's size and structure. In massive hot stars, fusion occurs rapidly in a small core, generating enormous energy that pushes outward against gravity and inflates the star to gigantic proportions. In smaller, cooler stars like Proxima Centauri, fusion proceeds much more slowly, producing less energy and allowing gravity to compress the star into a smaller, denser configuration. Red dwarfs represent the minimum mass required for a star to sustain hydrogen fusion, the primary nuclear reaction that powers most stars. Below a certain mass threshold, roughly 8% the mass of our Sun, a ball of gas lacks the core temperature and pressure needed to fuse hydrogen into helium. Such objects are called brown dwarfs, failed stars that glow dimly from residual heat left over from their formation but cannot sustain the nuclear fires that define true stars. Proxima Centauri sits just above this critical threshold, with a mass approximately 12% that of our Sunday. This seemingly small difference between 12% and 8% separates a true star capable of shining for trillions of years from a brown dwarf that will gradually cool and fade over mere billions of years. The internal structure of red dwarf stars differs fundamentally from that of larger stars like the Sunday. Our Sun has a radiative core where energy is transported outward through the absorption and re-emission of photons, surrounded by a convective envelope where hot gas physically rises and cool gas sinks, creating circulation patterns similar to boiling water. Red dwarfs like Proxima Centauri are fully convective throughout their entire volume. Hot plasma rises from the core to the surface, cools, and sinks back down in a continuous churning motion that mixes the star's material thoroughly. This complete mixing has profound implications for the star's lifespan and behavior. In stars like the Sun, only the hydrogen in the core gets fused into helium, leaving the outer layers untouched. When the core hydrogen is exhausted, the Sun will begin fusing helium and eventually shed its outer layers as a planetary nebula, leaving behind a white dwarf remnant Red dwarfs, by contrast, have access to all their hydrogen fuel through convective mixing, allowing them to burn at an incredibly slow rate for trillions of years, far longer than the current age of the universe. The fully convective nature of red dwarfs also makes them incredibly active and violent compared to what their small size might suggest. Proxima Centauri is notorious for its flaring activity, sudden eruptions where the star's brightness can double or triple within minutes before fading back to normal. These flares are caused by magnetic field interactions in the star's convective envelope. As plasma circulates through the star, it carries magnetic fields that become tangled and twisted, building up energy until they suddenly reconnect in violent releases that heat portions of the stellar surface to extreme temperatures. On Proxima Centauri, these flares are particularly intense because the star's complete convection generates powerful magnetic fields throughout its entire volume. Some flares on Proxima Centauri have been observed to release as much energy in a few minutes as the star normally emits in an entire day. For any planets orbiting this star, such flares would be catastrophic, bathing them in intense radiation and potentially stripping away their atmospheres over time. This violent behavior makes red dwarfs paradoxical objects. They are the smallest, coolest, and longest-lived stars. Yet they are also among the most magnetically active and potentially hostile to life on nearby planets. Understanding the physical processes that govern red dwarf stars required decades of theoretical work and observational confirmation. In the mid-20th century, astrophysicists developed the Standard Model of Stellar Structure, a set of equations describing how gas pressure, radiation pressure, gravity, and energy transport interact inside stars. These equations, combined with knowledge of nuclear fusion rates and the properties of matter under extreme conditions, allowed scientists to construct theoretical models of stars with different masses and compositions. When these models were applied to stars with masses around 12% that of the Sun, they predicted objects with radii roughly 14% of the Sun's radius and surface temperatures around 3,000 degrees. These predictions matched the observed properties of Proxima Centauri remarkably well, giving astronomers confidence that they understood the basic physics of red dwarf stars. However, refining these models to account for the complex effects of magnetic fields, stellar rotation, and convective mixing remained an ongoing challenge. Even today, with sophisticated computer simulations and detailed observations from space telescopes, our understanding of red dwarf stars continues to evolve as new observations reveal unexpected behaviors and properties. Measuring the unmeasurable. Determining the size of a star separated from us by trillions of miles presents one of astronomy's greatest technical challenges. We cannot stretch a measuring tape across interstellar space, and even our most powerful telescopes cannot resolve Proxima Centauri as anything more than a point of light. The star's angular size in the sky is so tiny that it would be like trying to measure the width of a human hair from a distance of several miles. Direct measurement through imaging is impossible with current technology, so astronomers must use indirect methods that infer the star's size from other measurable properties. The fundamental relationship that makes this possible is the Stefan-Boltzmann law, which connects a star's luminosity, temperature, and radius. Luminosity is the total amount of energy a star emits per second, temperature is the average energy of particles at its surface, and radius is the physical size we want to determine. The Stefan-Boltzmann law tells us that luminosity increases with the square of the radius and the fourth power of the temperature, meaning a small increase in temperature causes a large increase in luminosity, while doubling the radius only quadruples the luminosity. By measuring a star's luminosity and temperature, astronomers can calculate its radius using this relationship. Measuring the luminosity of Proxima Centauri, requires knowing two things: its apparent brightness, as seen from Earth, and its distance. Apparent brightness is relatively easy to measure using sensitive detectors that count photons arriving from the star. Distance measurement is more challenging, but benefits from Proxima Centauri being the closest star to our solar system. Modern parallax measurements from satellites like Hipparcos and Gaia have determined the distance to Proxima Centauri with extraordinary precision, placing it at approximately 4.24 light-years from Earth, or about 40 trillion kilometers. With this distance known, astronomers can calculate the star's true luminosity from its apparent brightness using the inverse square law, which states that light spreads out as it travels through space, decreasing in intensity proportional to the square of the distance. The calculations reveal that Proxima Centauri has a luminosity about 0.17% that of our Sun, making it one of the faintest stars known. This incredibly low luminosity tells us immediately that the star must be either very small, very cool, or both. Determining the temperature of Proxima Centauri's surface involves analyzing its spectrum, the rainbow of colors produced when starlight is split by a prism or diffraction grating. Every element and molecule absorbs and emits light at specific wavelengths, creating a unique fingerprint in the star's spectrum. By identifying these spectral features, astronomers can determine which chemicals are present in the star's atmosphere and how hot that atmosphere must be for those chemicals to produce the observed pattern. Proxima Centauri's spectrum is dominated by absorption lines from molecules like titanium oxide, which are only stable at temperatures below about 4,000 degrees Celsius. The overall shape of the spectrum, showing a peak in the infrared portion rather than visible light, indicates a surface temperature around 3,000 degrees. This is remarkably cool compared to stars like our Sun, which has a surface temperature of about 5,500 degrees, or blue giant stars that can exceed 30,000 degrees. With both luminosity and temperature measured, the Stefan-Boltzmann law allows astronomers to calculate that Proxima Centauri has a radius approximately 14% that of our Sun, or roughly 1.5 times the radius of Jupiter. These numbers reveal the first profound insight into Proxima Centauri's true size. Despite being a star capable of nuclear fusion, it is only slightly larger than Jupiter, the biggest planet in our solar system. Jupiter has a radius of about 70,000 kilometers, while Proxima Centauri's radius is approximately 100,000 kilometers. To put this in perspective, you could fit about 7 Proxima Centauri stars side by side across the diameter of our Sunday. The star's volume is roughly 3% that of the Sun, meaning you could fit about 36 Proxima Centauri stars inside our Sun with room to spare. Yet despite being so small, Proxima Centauri has about 150 times the mass of Jupiter and 12% the mass of the Sunday. This apparent contradiction between size and mass reveals another crucial aspect of the star's nature. It is incredibly dense. While Jupiter is mostly hydrogen and helium gas, with a density only slightly greater than water, Proxima Centauri's interior is compressed to densities dozens of times greater than lead, squeezed by gravity, and heated to temperatures of millions of degrees, where nuclear fusion can occur. The star's small size is not a sign of weakness, but a consequence of the delicate balance between the inward crush of gravity and the outward push of fusion energy for a star with relatively little mass. Refining these measurements has been an ongoing effort spanning decades of astronomical research. Early estimates of Proxima Centauri's size were rough approximations based on limited data and simplified theoretical models. As observational techniques improved and theoretical understanding deepened, astronomers revised their estimates, gradually converging on the values we accept today. One breakthrough came from interferometry, a technique that combines light from multiple telescopes to achieve the resolving power of a much larger instrument. While even interferometry cannot directly image Proxima Centauri's disk, it can measure subtle effects like gravitational microlensing or constrain the star's angular size enough to improve radius estimates. Another advance came from studying eclipsing binary star systems containing red dwarfs similar to Proxima Centauri. When two stars orbit each other and pass in front of one another from our perspective, astronomers can measure the duration and depth of the eclipses to determine the stars' sizes directly. By studying many such systems and comparing them to theoretical models, astronomers refined their understanding of the mass-radius relationship for red dwarfs, confirming that stars with Proxima Centauri's mass should indeed have radii around 14% that of the Sunday. The mass mystery. Understanding the size of Proxima Centauri requires understanding its mass, because mass is the fundamental property that determines everything else about a star. A star's mass dictates how strongly gravity compresses its core, which determines the core temperature and pressure, which in turn controls the rate of nuclear fusion. Fusion rate determines how much energy the star produces, which affects its luminosity and how much thermal pressure pushes outward against gravity, ultimately setting the star's radius and surface temperature. Every property of a star flows from its mass, making mass measurement absolutely critical for understanding stellar structure. For stars in binary systems where two stars orbit each other, astronomers can measure mass directly using Kepler's laws of orbital motion. By observing how quickly the stars orbit and how far apart they are, astronomers can calculate the total mass of the system with high precision. Proxima Centauri presents a unique challenge because while it is part of the Alpha Centauri triple star system, it orbits the central binary pair at such a vast distance that its orbital period is roughly 500,000 years, far too long for astronomers to observe any significant portion of an orbit. Without direct orbital measurements, astronomers must estimate Proxima Centauri's mass using indirect methods based on its other properties and comparisons to similar stars. One approach uses the star's luminosity and theoretical mass-luminosity relationships derived from stellar models. Astrophysicists have constructed detailed computer models of red dwarf stars with different masses, calculating how these models would appear if observed from Earth. By comparing Proxima Centauri's observed properties to these models, astronomers can estimate which mass value produces the best match. These calculations suggest a mass roughly 12% that of our Sun, or about 123 times the mass of Jupiter. Another method examines the star's spectrum in detail, looking for subtle features that depend on surface gravity, which is determined by the star's mass and radius. Higher surface gravity causes spectral lines to broaden through a process called pressure broadening, where collisions between atoms in the dense stellar atmosphere affect the wavelengths of light they absorb and emit. By measuring this broadening and combining it with the estimated radius, astronomers can calculate the surface gravity and thus infer the mass. The mass of Proxima Centauri, while small compared to the Sun, is still enormous by terrestrial standards. To put this in perspective, consider that our entire planet Earth has a mass of roughly 6 trillion kilograms, or 6 times 10 to the 24th power kilograms. Proxima Centauri's mass is approximately 240,000 trillion kilograms, or 2.4 times 10 to the 29th power kilograms. This means Proxima Centauri contains about 40,000 Earth masses squeezed into a sphere only slightly larger than Jupiter. The average density throughout the star is roughly 27 times the density of water, comparable to the density of iron or nickel, even though the star is made almost entirely of hydrogen and helium. This remarkable density arises because gravity compresses the gas to extreme pressures, packing atoms far closer together than they can be in any terrestrial material. At the star's core, where temperatures exceed 10 million degrees and pressures reach billions of atmospheres, matter exists in a state completely foreign to our everyday experience. A plasma so hot and dense that atoms are stripped of their electrons, and quantum mechanical effects become important in determining how particles behave. The relationship between mass and size for red dwarf stars is not straightforward or intuitive. You might expect that doubling a star's mass would double its radius, just as doubling the amount of water you pour into a balloon makes the balloon bigger. But stars do not behave this way because they are self-gravitating objects in hydrostatic equilibrium, where every layer of gas supports the weight of the layers above it through pressure. Adding more mass to a star increases the gravitational force trying to compress it, which increases the pressure needed to support that mass, which increases the temperature, which increases the fusion rate and energy output. All these effects interact in complex ways that cause the mass-radius relationship to be non-linear. For red dwarfs in particular, increasing mass actually increases radius more slowly than you might expect, because the increased fusion rate produces more energy that inflates the star, but the increased gravity compresses it more strongly. The result is that red dwarfs with twice the mass of Proxima Centauri are not twice as large, but only about 70% larger. Conversely, red dwarfs with half Proxima's mass, barely above the minimum mass for hydrogen fusion, are only about 30% smaller, not 50% smaller. This unusual mass-radius relationship means that Proxima Centauri's size is constrained within a fairly narrow range by the fundamental physics of low-mass stars. Recent advances in measuring red dwarf masses have come from the discovery of thousands of exoplanets, planets orbiting stars other than our Sunday. When a planet orbits a star, both the planet and star actually orbit their common center of mass, causing the star to wobble slightly. By measuring this wobble through precise observations of the star's motion, astronomers can determine the planet's mass and also constrain the star's mass using Newton's laws of motion. For red dwarfs with detected planets, this technique provides independent mass measurements that can be compared to estimates from stellar models, helping to calibrate and improve those models. Several red dwarfs, similar to Proxima Centauri, have been studied this way, and the results generally confirm that stars with Proxima's luminosity and temperature do indeed have masses around 12% that of the Sunday. These measurements also revealed that some red dwarfs were more massive or less massive than models predicted based on their luminosity alone, pointing to the influence of factors like chemical composition, age, and magnetic field strength that theoretical models must account for. The ongoing refinement of red dwarf mass measurements represents an active area of research with implications not just for understanding Proxima Centauri, but for characterizing the most common type of star in the galaxy, the radius revelation. After years of indirect measurements and theoretical calculations, astronomers can confidently state that Proxima Centauri has a radius approximately 1.2 times that of Jupiter, or roughly 107,000 kilometers. For comparison, our Sun has a radius of about 696,000 kilometers, making Proxima Centauri just under 15% the Sun's radius. To visualize this size difference, imagine the Sun as a large exercise ball, about 2 feet in diameter. On this scale, Proxima Centauri would be roughly the size of a tennis ball, while Earth would be about as big as a peppercorn. Despite the star's small physical size, its radius represents a crucial threshold in astrophysics. Objects smaller than about 70,000 kilometers in radius, with masses below 8%, the Sun's mass cannot achieve the core temperatures necessary for sustained hydrogen fusion, and are classified as brown dwarfs rather than true stars. Proxima Centauri sits comfortably above this limit with a radius 50% larger than the minimum required for hydrogen fusion, ensuring that it will continue burning its hydrogen fuel for trillions of years to come. The discovery that Proxima Centauri is barely larger than Jupiter shocked many people when they first encountered this fact. We think of stars as huge cosmic furnaces, blazing infernos vastly larger than anything in our solar system. Finding that the nearest star to our Sun is actually comparable in size to our solar system's largest planet challenges our intuitive sense of what stars should be. But size and nature are not always correlated in astronomy. Jupiter, despite its impressive size, is a cold ball of gas with an interior temperature of perhaps 20,000 degrees at most, far too cool for nuclear fusion. Proxima Centauri, though only slightly larger, has a core temperature exceeding 10 million degrees, hot enough to fuse hydrogen nuclei together and release the energy that makes it shine. The crucial difference is mass. Jupiter contains only about 0.1% the mass of the Sun, while Proxima Centauri contains 12% of the Sun's mass, over 100 times more massive than Jupiter. This extra mass provides the gravitational compression needed to heat the core to fusion temperatures, transforming what would otherwise be a gas giant planet into a genuine star. Understanding Proxima Centauri's radius has important implications for characterizing the planets that orbit it, particularly Proxima Centauri b, a rocky planet discovered in 2016, orbiting in the star's habitable zone, where liquid water could exist on the surface. When a planet passes in front of its star from our perspective, it blocks a small fraction of the star's light, creating a mini eclipse called a transit. The depth of this transit, the amount of light blocked, depends on the ratio of the planet's area to the star's area. Since area scales with the square of the radius, a planet transiting a small star, like Proxima Centauri, blocks more light than the same planet would block transiting a larger star, like the Sunday. This makes planets around red dwarfs easier to detect and characterize through transit observations. However, Proxima Centauri's flaring activity and the edge-on orbital geometry required for transits make such observations challenging. Astronomers discovered Proxima Centauri b not through transits but through radial velocity measurements, detecting the tiny wobble the planet induces in the star's motion. Knowing the star's mass and radius helps astronomers calculate what properties the planet must have to produce the observed wobble, leading to estimates that Proxima Centauri b has a mass at least 1.3 times Earth's mass, and likely a rocky composition similar to our planet. The physical structure of a star with Proxima Centauri's radius is remarkably different from the structure of larger stars. Our Sun has distinct layers with different properties: a core where fusion occurs, extending about 25% of the Sun's radius, a radiative zone where energy is transported by photons, a convective zone where hot gas circulates, and a thin photosphere that we see as the Sun's surface. Proxima Centauri has no such layered structure. The entire star is convective, with hot plasma rising from the fusion region at the center to the surface, releasing its energy, cooling, and sinking back down. This complete mixing means that fresh hydrogen fuel is constantly brought from the outer layers to the core, while fusion products like helium are carried throughout the star rather than accumulating in the center. The convective motion is driven by temperature differences between the hot interior and cooler surface, creating circulation patterns similar to Earth's atmospheric weather, but on a vastly larger scale. Computer simulations of these convection patterns reveal complex three-dimensional flows with rising and falling columns of plasma, horizontal flows near the surface, and rotation-induced circulation patterns that generate the star's powerful magnetic field. The surface of Proxima Centauri, like all stars, is not a solid boundary, but rather the photosphere, the layer from which light can escape into space. Below this layer, the gas is so dense and opaque that photons are constantly absorbed and re-emitted, taking millions of years to random walk from the core to the surface. Above this layer, the gas is thin enough that photons can travel freely through space. The photosphere of Proxima Centauri has a temperature around 3,000 degrees Celsius and a density about 1/1,000,000th that of Earth's atmosphere at sea level, comparable to the vacuum in high-altitude physics experiments. Despite this thinness, the photosphere is where the star's spectrum is formed, where absorption lines from atoms and molecules imprint their signatures on the light we observe. Above the photosphere lies the chromosphere, a layer of hotter, more rarefied gas visible during the star's frequent flares, when magnetic energy heats portions of the atmosphere to tens of thousands of degrees. Observations of Proxima Centauri in ultraviolet and X-ray wavelengths reveal this chromospheric activity, showing how the star's magnetic field threads through the atmosphere, storing energy that explosively releases during flare events. Understanding these surface layers and their dynamics is crucial for assessing the habitability of planets like Proxima Centauri b, which orbits close enough to the star that it experiences the full brunt of its magnetic fury. Comparing sizes across the cosmos. To truly appreciate how big Proxima Centauri is, we must place it in context by comparing it to other objects in the universe, from the smallest asteroids to the largest known stars. This journey across cosmic size scales reveals where Proxima Centauri fits in the grand hierarchy of objects and helps us understand why its particular size is so significant. Starting small, consider that atoms are about 1/10,000,000,000th of a meter in diameter, far too tiny to see, even with the most powerful microscopes. A grain of sand is roughly 1 millimeter across, containing trillions of atoms. Earth, our home planet, has a diameter of about 12,700 kilometers, large enough to fit more than 1 million Earths inside the Sunday. Jupiter, the giant of our solar system, has a diameter about 11 times Earth's, or approximately 140,000 kilometers, making it more than 1,000 times the volume of Earth. Proxima Centauri's diameter of roughly 214,000 kilometers is only about 50% larger than Jupiter's, showing that the smallest stars are remarkably similar in size to the largest planets. This similarity is not coincidental, but reflects fundamental limits imposed by the physics of how gravity compresses matter. Moving up the size scale, our Sun has a diameter of about 1.4 million kilometers, making it about 6.5 times larger than Proxima Centauri in diameter, or about 280 times larger in volume. You could fit about 280 Proxima Centauri stars inside the Sun, though packing spheres always leaves empty space, so the actual number would be somewhat less. The Sun represents a medium-sized star, neither particularly large nor small compared to the full range of stellar sizes. Many stars in our galaxy are similar to the Sun in size and mass, but even more are smaller red dwarfs like Proxima Centauri. In fact, about 75% of all stars in the Milky Way galaxy are red dwarfs, making Proxima Centauri's size class the most common type of star. This means that if we randomly selected a star from our galaxy, the chances are 3 in 4 that it would be comparable to or smaller than Proxima Centauri. The Sun, despite seeming normal to us, is actually larger and brighter than most stars, placing it in the top 30% by size and luminosity. On the upper end of the stellar size spectrum lie the giant and supergiant stars, objects so enormous that they dwarf even our Sunday. A red giant star like Arcturus, one of the brightest stars visible from Earth, has a radius about 25 times that of the Sun, or about 170 times the radius of Proxima Centauri. If Arcturus were placed at the center of our solar system, its surface would extend beyond the orbit of Venus, engulfing Mercury and making Earth's orbit just barely outside the star's atmosphere. Even this is modest compared to the true giants. Betelgeuse, the red supergiant in the constellation Orion, has a radius estimated at about 900 times the Sun's radius, or 6,000 times Proxima Centauri's radius. If Betelgeuse replaced our Sun, its surface would extend beyond the orbit of Jupiter, swallowing Earth, Mars, and the asteroid belt. The largest known star, UY Scuti, has a radius approximately 1,700 times the Sun's radius, or about 11,000 times Proxima Centauri's radius. Placed at the center of our solar system, UY Scuti would extend nearly to the orbit of Saturn, its volume so vast that it could contain 5 billion suns, or 1.4 trillion Proxima Centauri stars. These comparisons reveal that Proxima Centauri sits at the extreme low end of the stellar size spectrum, tiny compared to giants and supergiants, yet still distinctly a star rather than a planet or brown dwarf. The enormous range of stellar sizes, spanning factors of thousands between the smallest red dwarfs and the largest supergiants, raises a fundamental question. Why do stars come in such different sizes? The answer lies in how stars form and evolve. Stars begin as clouds of gas and dust in space that collapse under their own gravity. As the cloud contracts, it heats up, and if enough mass accumulates in the center, the core temperature rises high enough to ignite hydrogen fusion. The mass of gas that manages to collapse and form a single star depends on the initial cloud's properties and the fragmentation process that breaks large clouds into smaller pieces. Low-mass regions form small stars like Proxima Centauri, while high-mass regions form large stars. Once formed, a star's evolution depends critically on its mass. Low-mass stars burn their fuel slowly and change very little over billions of years, remaining small and cool throughout their lifetimes. High-mass stars burn their fuel rapidly and evolve quickly, expanding into giants and supergiants as they exhaust their core hydrogen and begin fusing heavier elements. The size differences between stars also reflect differences in their life stages. Proxima Centauri is a main sequence star, stably fusing hydrogen into helium in its core, and will remain in this phase for trillions of years due to its low mass and slow fusion rate. The Sun is also a main sequence star, but will remain in this phase for only about 10 billion years total, having already consumed about half its core hydrogen over the past 4.6 billion years. When the Sun exhausts its core hydrogen, it will evolve off the main sequence, expanding into a red giant with a radius about 200 times its current size, large enough to engulf Earth. This red giant phase will last about 1 billion years before the Sun sheds its outer layers and collapses into a white dwarf, a stellar remnant about the size of Earth but with roughly half the Sun's mass compressed into a volume no larger than a planet. Proxima Centauri will never undergo such dramatic evolution. Its low mass means it will burn through all its hydrogen incredibly slowly, remaining a red dwarf for perhaps 4 trillion years, roughly 300 times the current age of the universe. Eventually, it will transition to fusing helium, but theoretical models suggest it will never expand significantly or produce a planetary nebula like the Sun will. Instead, it will gradually fade, eventually becoming a white dwarf composed primarily of helium rather than carbon and oxygen like solar mass white dwarfs. The density difference. While Proxima Centauri is small compared to most stars and only slightly larger than Jupiter in radius, its density tells a very different story. Density is mass divided by volume, a measure of how much matter is packed into a given amount of space. Jupiter, despite its enormous size, is mostly made of hydrogen and helium gas, with an average density only about 1.3 times the density of water, or roughly 1.3 grams per cubic centimeter. This low density is characteristic of gas giant planets, which do not have sufficient mass to compress their material to high densities. Proxima Centauri, with about 150 times Jupiter's mass, but only about 3.4 times its volume, has an average density of approximately 40 times that of Jupiter, or roughly 55 grams per cubic centimeter. This is more than 5 times the density of iron and about 40 times the density of water, indicating that the star's interior is compressed to pressures and temperatures far beyond anything achievable in laboratories on Earth. The density distribution within Proxima Centauri is not uniform. Like all stars, Proxima Centauri is densest at its center and becomes progressively less dense toward the surface. At the core, where temperatures exceed 10 million degrees and nuclear fusion converts hydrogen to helium, the density reaches approximately 150 grams per cubic centimeter, roughly 15 times the density of lead. Under these extreme conditions, matter exists as a plasma, where electrons are stripped from atomic nuclei, and the nuclei themselves are packed closely together, separated by distances comparable to the size of the nuclei themselves. Quantum mechanical effects become important in such dense matter, with the Pauli exclusion principle preventing electrons from occupying the same quantum states and providing additional pressure support against gravitational collapse. This degeneracy pressure is the same force that supports white dwarf stars against collapse even after they have exhausted their nuclear fuel. In Proxima Centauri's core, degeneracy pressure provides only a minor contribution to the total pressure, with most support coming from thermal pressure generated by the high temperature. But even this small contribution affects the star's structure and evolution. Moving outward from the core, the density decreases as we approach the surface. In the middle layers of the star, at about half the radius, the density is roughly 10 grams per cubic centimeter, similar to the density of silver or lead. In the outer layers, closer to the surface, the density drops to about 1 gram per cubic centimeter, comparable to water, and finally, to a tiny fraction of a gram per cubic centimeter in the photosphere where light escapes. This density gradient drives the convective circulation that characterizes red dwarf stars. Hot, buoyant plasma from the deep interior rises toward the surface, expands and cools as it encounters lower pressure, then sinks back down when it becomes denser than the surrounding material. The timescale for this circulation is surprisingly short. Computer models suggest that a parcel of gas can travel from the center of Proxima Centauri to the surface and back in only a few months, meaning the entire star is thoroughly mixed on timescales of a year or so. This rapid mixing is both a blessing and a curse for the star. The blessing is that fresh hydrogen fuel is constantly supplied to the fusion region, allowing the star to burn for trillions of years. The curse is that this vigorous convection also generates powerful magnetic fields that drive the intense flaring activity that makes the star a challenging environment for life. The high density of Proxima Centauri compared to Jupiter illustrates a fundamental principle of astrophysics. Mass is more important than size in determining an object's nature. Jupiter and Proxima Centauri have similar radii because both are roughly the size that self-gravitating balls of hydrogen and helium naturally assume given their respective masses. Jupiter's lower mass means gravity compresses the gas to pressures that are high by terrestrial standards, but insufficient to trigger nuclear fusion. The core temperature is only about 20,000 degrees, far below the 10 million degrees needed for hydrogen fusion. Proxima Centauri's higher mass compresses the gas to much greater pressures and densities, heating the core to fusion temperatures and transforming the object from a planet into a star. There is a gray zone between planets and stars occupied by brown dwarfs, objects with masses between about 13 times Jupiter's mass and about 80 times Jupiter's mass. Brown dwarfs can fuse deuterium, a heavy form of hydrogen, but cannot sustain fusion of ordinary hydrogen. Their cores reach temperatures of a few million degrees, hot enough for deuterium fusion but too cool for the much more abundant ordinary hydrogen to fuse. Brown dwarfs are dim objects, glowing mostly in infrared from the heat left over from their formation and the small amount of energy released by deuterium fusion early in their lives. Understanding density is also crucial for interpreting observations of exoplanets around red dwarf stars. When a planet transits a star, the depth of the transit depends on the ratio of the planet's area to the star's area. Combined with radial velocity measurements that give the planet's mass, astronomers can calculate the planet's density. A low density suggests a gas giant like Jupiter, while a high density indicates a rocky planet like Earth. For planets orbiting small stars like Proxima Centauri, these density measurements are particularly precise because the small stellar radius means planets block a larger fraction of the star's light, producing deeper, more easily measured transits. Several rocky planets have been discovered around nearby red dwarfs, including TRAPPIST-1, a star even smaller than Proxima Centauri that hosts 7 Earth-sized planets. Density measurements of these planets show that they are rocky worlds with compositions similar to Earth, suggesting that terrestrial planet formation is common around red dwarf stars. These discoveries have profound implications for the search for life beyond Earth, suggesting that habitable zone rocky planets may be more common around red dwarfs than around sun-like stars, simply because red dwarfs are so much more numerous. The temperature gradient. Temperature is one of the most fundamental properties defining a star's character, influencing its color, spectrum, size, and fate. Proxima Centauri's surface temperature of approximately 3,000 degrees Celsius places it among the coolest known stars, giving it a deep red color visible in telescopic images. To understand what this temperature means, we can compare it to familiar terrestrial temperatures. Water boils at 100 degrees Celsius, steel melts at around 1,500 degrees, and the hottest welding torches reach about 3,000 degrees. Proxima Centauri's surface is about as hot as an arc welding flame, hot enough to vaporize any solid material instantly, but cool enough that complex molecules can exist in its atmosphere. This relatively low temperature is both a cause and consequence of the star's small size. The low temperature means the star emits most of its light in the infrared rather than visible wavelengths, making it appear dim despite being relatively close to Earth. The small size is a consequence of the star's low mass, which produces only modest fusion energy, requiring less thermal pressure to balance gravity. The temperature inside Proxima Centauri increases dramatically as we move from the surface to the center, creating a steep temperature gradient that drives convective circulation. Just below the visible surface, in the upper atmosphere, temperatures are relatively cool, perhaps 2,000 degrees, allowing molecules like titanium oxide and water vapor to form. These molecules absorb light at specific wavelengths, creating the dark bands visible in the star's spectrum. Moving deeper, we encounter the convective envelope, where temperature increases rapidly with depth. At about 50% of the star's radius, roughly 50,000 kilometers below the surface, temperatures reach about 5 million degrees, hot enough to completely ionize all atoms into free electrons and nuclei. At this temperature, matter behaves as a fully ionized plasma with properties described by magnetohydrodynamics, the physics of electrically conducting fluids in magnetic fields. The magnetic fields, generated by convective motions at these depths, store enormous amounts of energy that can be released suddenly during flares, causing transient brightening and intense radiation. At the center of Proxima Centauri, temperatures exceed 15 million degrees, hot enough for nuclear fusion to convert hydrogen into helium. The fusion process requires that hydrogen nuclei, which are simply protons with positive electric charge, collide with sufficient energy to overcome their mutual electric repulsion and get close enough for the strong nuclear force to bind them together. At 15 million degrees, particles move fast enough that occasional collisions achieve the necessary energy, though most collisions still do not result in fusion. The fusion rate is therefore quite slow, with each proton in the core waiting billions of years on average before participating in a fusion reaction. This slow rate is precisely what allows Proxima Centauri to shine for trillions of years. Stars like the Sun, with hotter cores, burn through their fuel much faster, while brown dwarfs with cooler cores cannot sustain hydrogen fusion at all. Proxima Centauri occupies the sweet spot, where the core is just hot enough for fusion to occur, but not so hot that the fuel burns rapidly. The specific fusion reactions occurring in Proxima Centauri's core follow what is called the proton-proton chain, a sequence of nuclear reactions that ultimately converts 4 hydrogen nuclei into 1 helium nucleus plus energy. The first step involves 2 protons fusing to form a deuterium nucleus, a positron, and a neutrino. This is the slowest step because it requires 1 proton to transform into a neutron via the weak nuclear force, a quantum process that occurs very rarely. Once deuterium forms, it quickly captures another proton to form helium-3, a light isotope of helium. 2 helium-3 nuclei then fuse to form helium-4 and release 2 protons. The net result is that 4 protons are converted into 1 helium-4 nucleus, 2 positrons, 2 neutrinos, and energy in the form of gamma-ray photons. The mass of the helium nucleus is slightly less than the combined mass of 4 protons, and this missing mass is converted to energy according to Einstein's famous equation E equals mc squared. The energy released per fusion reaction is about 27 million electron volts, a tiny amount by human standards, but enough to power the star when multiplied by the trillions upon trillions of fusion reactions occurring every second. The temperature gradient from surface to core is maintained by the balance between energy generation in the core and energy loss from the surface. Energy produced by fusion in the core heats the surrounding gas, causing it to expand and rise. As it rises, it moves to regions of lower pressure and temperature, eventually reaching the surface, where it radiates energy into space as light and cools. The cooled gas then sinks back toward the center, completing the convective cycle. This process transports energy from the hot core to the cool surface much more efficiently than radiative diffusion, where photons random walk outward by being repeatedly absorbed and re-emitted. In larger stars like the Sun, radiative transport dominates in the core and inner layers, with convection only taking over in the outer envelope. Proxima Centauri's complete convection means that temperature gradients are relatively gentle compared to radiative zones, where temperature can drop dramatically over short distances. This gentle gradient is crucial for maintaining the convective circulation that defines the star's structure and behavior, luminosity and energy output. When we discuss how big a star is, we often focus on physical dimensions like radius and mass, but luminosity provides another crucial measure of a star's significance in the universe. Luminosity is the total amount of energy a star emits per second across all wavelengths of light, from radio waves to gamma rays. Our Sun has a luminosity of approximately 3.8 times 10 to the 26th watts, equivalent to the power output of about 10 octillion 100-watt light bulbs. Proxima Centauri has a luminosity of only about 6.5 times 10 to the 23 watts, roughly 1/6 of 1%, the Sun's luminosity, or about 1/600th as bright. This enormous difference in luminosity, despite the stars being physically somewhat similar in size, reflects the strong dependence of energy output on mass and temperature. Small differences in these properties produce large differences in luminosity, making Proxima Centauri thousands of times fainter than the Sun, even though it is only about 7 times smaller in radius. The low luminosity of Proxima Centauri has profound implications for any planets orbiting the star. A planet receiving the same amount of energy as Earth receives from the Sun would need to orbit Proxima Centauri at a distance of only about 7 million kilometers, roughly 5% the distance from Earth to the Sunday. At this distance, the planet would orbit the star every 11 days, completing more than 30 orbits per Earth year. This close orbit places the planet well within what astronomers call the habitable zone, the range of distances where liquid water could exist on a planet's surface given the right atmospheric conditions. Proxima Centauri b, the rocky planet discovered orbiting the star, lies within this habitable zone, sparking intense interest in whether it could potentially harbor life. However, orbiting so close to the star exposes the planet to intense stellar flares and high-energy radiation, potentially stripping away its atmosphere and sterilizing the surface. The question of whether life could survive, let alone thrive, on a planet around such an active star remains hotly debated among astrobiologists. The spectrum of Proxima Centauri's light output is dramatically different from that of the Sun due to the star's lower surface temperature. The Sun emits most of its energy in visible light, with peak emission in the green-yellow part of the spectrum around 500 nanometers wavelength. This is why the Sun appears yellow-white to our eyes and why plants on Earth evolved to harvest visible light for photosynthesis. Proxima Centauri, with its cooler surface temperature, emits most of its energy in the infrared part of the spectrum, beyond 1,000 nanometers wavelength, invisible to human eyes. Less than 15% of the star's energy output is in visible light, which is why the star appears so faint despite being the closest stellar neighbor. If you could travel to a planet orbiting Proxima Centauri at a habitable distance, the sky would look very different from Earth's. The star would appear large in the sky, perhaps 3 times the angular size of the Sun as seen from Earth, but deep red in color, and surrounded by a faint reddish glow. The landscape would be bathed in infrared radiation, and plants photosynthesizing this light might appear black or very dark to absorb as many photons as possible rather than reflecting green light, like Earth's plants. Measuring the luminosity of Proxima Centauri requires accounting for the star's output across all wavelengths, not just the visible light that our eyes and optical telescopes detect. Ground-based telescopes can observe visible and near-infrared light, but Earth's atmosphere blocks many infrared wavelengths, requiring observations from space telescopes or high-altitude observatories. Ultraviolet and X-ray emissions are also blocked by the atmosphere and must be observed from space. When astronomers add up all these contributions, they find that Proxima Centauri emits most energy in the near-infrared around 1 to 2 micron wavelength, with smaller contributions from visible light, mid-infrared, ultraviolet, and X-rays. The ultraviolet and X-ray emission is particularly interesting because it comes primarily from the star's chromosphere and corona, heated to hundreds of thousands or millions of degrees by magnetic activity. During flares, the X-ray luminosity can increase by factors of 10 or more, briefly making X-rays a significant fraction of the star's total energy output. This high-energy radiation poses a severe threat to any life on nearby planets, as it can break chemical bonds in biological molecules and strip away planetary atmospheres over time. The energy budget of Proxima Centauri is intimately connected to its nuclear fuel supply and lifespan. The star contains about 12% the Sun's mass, or roughly 2.4 times 10 to the 29 kilograms of material. About 76% of this mass is hydrogen, the primary fuel for fusion, giving Proxima Centauri approximately 1.8 times 10 to the 29 kilograms of hydrogen fuel. The fusion reactions convert about 0.7% of this hydrogen mass into energy via Einstein's E equals mc squared equation, yielding a total available energy of roughly 1.2 times 10 to the 45 joules. Dividing this total energy by the star's luminosity of 6.5 times 10 to the 23 watts gives a fuel lifetime of approximately 1.8 times 10 to the 21 seconds, or about 58 trillion years. This is roughly 4,000 times the current age of the universe, which is about 13.8 billion years old. In reality, theoretical models suggest Proxima Centauri will shine for perhaps 4 trillion years before exhausting its hydrogen, still nearly 300 times the universe's current age. The discrepancy from the simple calculation arises because not all the hydrogen will be fused, and the star's luminosity may change as it ages, but the basic conclusion remains the same. Proxima Centauri is an extraordinarily long-lived star that has barely begun its lifespan. The color connection. The color of a star is one of its most immediately noticeable properties and is intimately connected to its temperature and size. Proxima Centauri appears deep red when viewed through a telescope powerful enough to separate it from the glare of the much brighter Alpha Centauri binary nearby. This red color is not an arbitrary aesthetic feature, but a direct consequence of the star's surface temperature of about 3,000 degrees. The connection between color and temperature comes from blackbody radiation, a fundamental law of physics stating that all objects emit electromagnetic radiation with a spectrum determined solely by their temperature. Hotter objects emit more radiation at shorter wavelengths, shifting the peak emission toward the blue end of the spectrum, while cooler objects emit more at longer wavelengths, shifting toward the red. The Sun, with its surface temperature of about 5,500 degrees, appears yellow-white because its emission peaks in the green part of the spectrum, but includes substantial blue and red light as well. Proxima Centauri's cooler surface shifts the emission peak into the infrared, with only the tail of the distribution extending into visible red wavelengths, giving the star its characteristic ruby color. Astronomers quantify stellar colors using a system of magnitude measurements through different color filters. The most common filters are B for blue light, V for visual or green-yellow light, and R for red light, along with infrared filters labeled I, J, H, and K for progressively longer wavelengths. By measuring a star's brightness through different filters and comparing the measurements, astronomers derive color indices like B-V or V-I that indicate the star's temperature. The Sun has a B-V color index of plus 0.6 to 5, indicating it is slightly brighter in visual light than blue light, characteristic of a yellow star. Proxima Centauri has a B-V color index of about plus 1.9, indicating it is much brighter in visual light than blue light, characteristic of a red star. Even more striking is the V-I color index of about 2.2, showing that Proxima Centauri is vastly brighter in the infrared I band than in the visual V band. These large color indices immediately tell astronomers that Proxima Centauri is a cool, red star without needing to analyze its spectrum in detail. The red color of Proxima Centauri has practical implications for observing the star and any planets around it. Because the star is so faint in visible light, early observations struggled to characterize it, and even today, detailed studies require large telescopes and long exposure times. However, the star's brightness in the infrared makes it an ideal target for infrared telescopes and instruments. The discovery of Proxima Centauri b was made primarily using visible light spectrographs detecting the star's radial velocity wobble, but follow-up studies to characterize the planet's atmosphere and search for additional planets increasingly rely on infrared observations. Infrared light also has the advantage of being less affected by stellar flares, which primarily increase the star's ultraviolet and visible light output. By observing in the infrared, astronomers can monitor the star more continuously and detect subtle planetary signals that might be masked by flare activity in visible light. Future missions to study exoplanets around nearby red dwarfs, including potential atmospheric characterization of Proxima Centauri b, will rely heavily on infrared space telescopes like the James Webb Space Telescope. The color of stars also provides information about their chemical composition, or metallicity as astronomers call it. In astronomical terminology, metals are all elements heavier than hydrogen and helium, including common elements like carbon, nitrogen, oxygen, and iron. Stars with higher metallicity tend to be slightly cooler and redder than stars of the same mass with lower metallicity, because metals increase the opacity of the stellar atmosphere, trapping more heat and forcing the star to expand slightly to transport the energy outward. Proxima Centauri has a metallicity about 85% that of the Sun, meaning it contains slightly fewer heavy elements relative to hydrogen. This lower metallicity is consistent with Proxima Centauri being an old star formed early in the galaxy's history when fewer heavy elements had been produced by previous generations of stars. However, the effect of this metallicity difference on the star's color is minor compared to the temperature effect. The star appears red primarily because it is cool, not because it is metal poor. More detailed spectroscopic studies can separate these effects by analyzing individual spectral lines from different elements, revealing the star's chemical fingerprint and providing clues about its formation, history, and age. Understanding the colors of stars like Proxima Centauri helps astronomers classify stars into a system that organizes them by temperature and spectral features. This system, called the Morgan-Keenan or MK classification, assigns stars letter codes based on their spectral appearance. The sequence runs O, B, A, F, G, K, M, from hottest to coolest, with O stars being blue and extremely hot, around 30,000 degrees or more, and M stars being red and cool, below 3,800 degrees. Each letter is subdivided into numbers from 0 to 9, with 0 being the hottest of that letter class and 9 the coolest. The Sun is classified as a G2 star, near the hot end of the G class. Proxima Centauri is classified as an M5.5 V star, where M indicates a red dwarf, 5.5 indicates a temperature about halfway through the M-class range, and V indicates a main sequence star still fusing hydrogen. The M5.5 classification places Proxima Centauri among the coolest of the normal red dwarfs, just above the transition to M6 stars that represent the coolest and smallest hydrogen-fusing stars. This classification immediately tells astronomers familiar with the system that Proxima Centauri is a cool, small, faint red dwarf with specific spectral features like strong titanium oxide absorption bands. The flaring fury. One of the most remarkable aspects of Proxima Centauri's behavior is its intense and frequent stellar flares, sudden eruptions where the star's brightness can increase dramatically over timescales of minutes to hours. These flares are far more energetic and common than the solar flares we observe on the Sun, reflecting the powerful magnetic fields generated throughout Proxima Centauri's fully convective interior. A typical flare on Proxima Centauri might increase the star's visible light output by a factor of 2 or 3, while the most intense flares can increase brightness by factors of 10 or more. In ultraviolet and X-ray wavelengths, the increases are even more dramatic, with the X-ray luminosity sometimes jumping by factors of 100 during major flare events. These eruptions release as much energy in a few minutes as the star normally emits over an entire day, creating brief but intense bursts of high-energy radiation that would bombard any nearby planets. The frequency of these flares is also striking. Observations show that Proxima Centauri produces detectable flares every few days on average, with smaller flares possibly occurring even more frequently, but remaining below detection thresholds. The physical mechanism driving these flares is magnetic reconnection, a process where magnetic field lines in the star's atmosphere become twisted and tangled, building up energy until they suddenly snap and reconnect in a new configuration, converting magnetic energy into heat and particle acceleration. In Proxima Centauri's case, the convective churning of plasma throughout the star's interior generates powerful magnetic fields through a process called the dynamo mechanism. Charged particles moving through the star's plasma generate electric currents, which in turn produce magnetic fields, and the convective motion twists and amplifies these fields into complex structures. Near the star's surface, magnetic field lines can emerge from the photosphere, creating loops and arches that extend into the corona. These magnetic structures store enormous amounts of energy, and when instabilities cause them to reconnect, the stored energy is released explosively. The reconnection heats portions of the corona to tens of millions of degrees, far hotter than the photosphere's mere 3,000 degrees, and accelerates electrons and protons to high velocities. These energetic particles then crash into the photosphere, heating it and causing the localized brightening we observe as a flare. The impact of these flares on any planets orbiting Proxima Centauri would be severe. Proxima Centauri b orbits at a distance of only about 7 million kilometers, roughly 20 times closer to its star than Earth is to the Sunday. At this distance, the planet receives the same average amount of energy as Earth, placing it in the habitable zone where liquid water could exist. However, during a major flare, the radiation flux could increase by an order of magnitude or more, exposing the planet's surface to intense ultraviolet and X-ray radiation. This high-energy radiation would break apart molecules in the planet's atmosphere, potentially stripping away atmospheric gases over time. Water vapor could be dissociated into hydrogen and oxygen, with the light hydrogen escaping to space while oxygen might be lost or react with surface rocks. Calculations suggest that over billions of years of exposure to such flares, a planet like Proxima Centauri b could lose an amount of atmosphere equivalent to Earth's oceans, raising serious questions about whether the planet could maintain habitable conditions. Despite these challenges, some scientists argue that life might still be possible on planets around flare stars like Proxima Centauri. One key factor is the planet's magnetic field. Earth's magnetic field shields our atmosphere from the solar wind, a stream of charged particles flowing from the sun, and helps protect the surface from cosmic radiation. If Proxima Centauri b has a strong magnetic field, it might deflect some of the charged particles accelerated during flares, reducing atmospheric erosion. Another protective factor could be a thick atmosphere. A dense atmosphere would absorb high-energy radiation in its upper layers, protecting the surface. Life in Earth's oceans is shielded from solar ultraviolet radiation by just a few meters of water, suggesting that subsurface or underwater life on Proxima Centauri b might survive even intense flares. Additionally, some organisms on Earth, called extremophiles, can survive high levels of radiation that would kill most life, suggesting that life around flare stars might evolve radiation-resistant biochemistry. The question of habitability around Proxima Centauri remains open, requiring detailed observations of the planet's atmosphere and magnetic environment to resolve. Observing and characterizing Proxima Centauri's flares provides valuable insights into the star's magnetic structure and behavior. Astronomers monitor the star continuously using networks of robotic telescopes that automatically alert researchers when a flare is detected, triggering follow-up observations with larger instruments. During a flare, the star's spectrum changes dramatically. Emission lines from hydrogen, calcium, and other elements become much stronger, indicating that these atoms are being excited by high-energy electrons and photons. The continuum emission, the background level of light across all wavelengths, also increases, showing that a larger area of the photosphere is being heated. By analyzing these spectral changes, astronomers can estimate the temperature, energy, and spatial distribution of the flare. Some observations have even resolved flares as distinct bright spots on the star's surface using interferometry, though the star's small angular size makes such observations extremely challenging. The long-term goal is to develop a comprehensive understanding of the magnetic activity cycle of Proxima Centauri, analogous to the 11-year sunspot cycle observed on the Sun, which would help predict flare occurrence and assess the long-term habitability environment for any planets. Mass versus volume. When we compare Proxima Centauri to our Sun or to Jupiter, one of the most striking revelations is the relationship between mass and volume. Jupiter has about 0.1% the Sun's mass, but about 10% the Sun's volume, giving it a very low average density. Proxima Centauri has about 12% the Sun's mass and only about 3% the Sun's volume, giving it a much higher average density than Jupiter, despite the two objects being similar in size. This mass-volume relationship reflects fundamental differences in internal structure. Jupiter is held together by gravity but lacks sufficient mass to compress its interior to fusion temperatures. The gas pressure increases with depth, but even at the center, the pressure is only a few million atmospheres, and the temperature only about 20,000 degrees. At these conditions, hydrogen remains molecular or atomic, not fully ionized, and occupies relatively large volumes because the electrons are still bound to protons rather than moving freely as in a plasma. Proxima Centauri, with its much higher mass, compresses its interior to pressures of billions of atmospheres and temperatures of millions of degrees, fully ionizing the hydrogen and allowing nuclear fusion to occur. The plasma state is much denser than neutral gas, packing more mass into a given volume. The mass-volume relationship also reveals the unusual nature of stellar physics compared to everyday experience. If you have 2 buckets of water and pour both into a larger container, the volume doubles while the mass doubles, maintaining constant density. Stars do not work this way. If you could magically add more mass to Proxima Centauri, the increased gravity would compress the existing material, increasing the density and temperature, which would increase the fusion rate and the outward pressure. The result would be a star that is more massive, but not proportionally larger. In fact, theoretical models show that doubling Proxima Centauri's mass to about 24%, the Sun's mass would increase its radius by only about 40%, to roughly 20% the Sun's radius, not doubling it as you might naively expect. Conversely, reducing Proxima Centauri's mass would decrease the radius, but not proportionally. At about 8% the Sun's mass, the minimum for hydrogen fusion, a star would have a radius only about 20% smaller than Proxima Centauri's, roughly 85,000 kilometers. Below this mass, brown dwarfs actually have nearly the same radius as the smallest hydrogen-fusing stars, despite having less mass, because the lack of fusion energy means gravity compresses them until electron degeneracy pressure, a quantum mechanical effect, provides support. This non-intuitive mass-volume relationship has important implications for understanding stellar evolution and the final states of stars. When massive stars exhaust their nuclear fuel and their cores collapse, they can form neutron stars with about 1.4 times the Sun's mass compressed into a sphere only about 20 kilometers in diameter, giving densities comparable to atomic nuclei. The mass-radius relationship for neutron stars is even more extreme than for red dwarfs, with increasing mass actually decreasing radius slightly, because the immense gravity overwhelms all forms of pressure except the degeneracy pressure of neutrons. For white dwarfs, the compact remnants of stars, like the Sun, increasing mass also decreases radius because electron degeneracy pressure obeys a specific equation of state where higher density provides more pressure, but at a rate that increases more slowly than the rate at which gravitational force increases with added mass. Eventually, at about 1.4 solar masses, the Chandrasekhar limit, a white dwarf can no longer support itself against gravity and will collapse, either forming a neutron star through a supernova explosion or accreting material that triggers a thermonuclear explosion called a Type Ia supernova. Proxima Centauri will never face such dramatic endpoints because its low mass means it will never ignite carbon fusion or undergo core collapse. Instead, after burning through its hydrogen fuel over trillions of years, it will gradually transition to fusing helium into carbon and oxygen in its core, maintaining hydrostatic equilibrium without dramatic expansion or instability. Eventually, when even helium is exhausted, the core will contract and heat while the outer layers expand slightly, but the star will not have enough mass to ignite carbon fusion. The core will settle into a state supported by electron degeneracy pressure, becoming a helium white dwarf with a mass similar to the current star's mass, but a radius only about 1%. The current radius? Roughly the size of Earth. The outer layers will slowly drift away over billions of years, so slowly that the process might take longer than the current age of the universe. This peaceful end contrasts sharply with the violent deaths of massive stars in supernova explosions, illustrating how mass determines not just a star's size during its life, but also its fate at death. Understanding the mass-volume relationship for red dwarfs like Proxima Centauri has practical applications for exoplanet research. When a planet transits a star, the depth of the transit depends on the ratio of areas, which is the square of the ratio of radii. To determine the planet's actual size from the transit depth, astronomers must know the star's radius accurately. For red dwarfs, where the mass-radius relationship is complex and depends on the star's age and composition, getting accurate radius measurements can be challenging. If the radius is underestimated, the planet's size will be underestimated as well, potentially leading to incorrect conclusions about whether the planet is rocky or gaseous. Recent studies combining transit observations with precise distance measurements from the Gaia satellite have improved red dwarf radius estimates, leading to revised sizes for many exoplanets. Some planets thought to be super-Earths, rocky worlds larger than Earth, turned out to be smaller when better stellar radii were available, while others became larger. These revisions matter for understanding planetary formation and evolution, as the distribution of planet sizes provides clues to how planets form and whether they retain or lose their atmospheres. The gravitational pull. Gravity is the fundamental force holding Proxima Centauri together, and the strength of gravity at the star's surface determines many of its observable properties. Surface gravity is defined as the gravitational acceleration an object would experience if placed at the star's surface, calculated using Newton's law of gravitation as G equals gm divided by r squared, where g is the gravitational constant, m is the star's mass, and r is its radius. For Proxima Centauri, with its mass about 12% the Sun's mass and radius about 14% the Sun's radius, the surface gravity works out to roughly 60 times Earth's surface gravity, or about 600 meters per second squared. For comparison, the Sun's surface gravity is about 28 times Earth's, so Proxima Centauri's surface gravity is more than twice the Sun's, despite the star being much smaller and less massive. This high surface gravity arises because gravity increases with mass, but decreases with the square of the radius, and Proxima Centauri's small radius more than compensates for its low mass. A person standing on the surface of Proxima Centauri, if such a thing were possible, would weigh 60 times their Earth weight, making movement impossible and causing immediate compression injuries. The high surface gravity of red dwarfs has important consequences for the structure and behavior of stellar atmospheres. In general, higher surface gravity means that atmospheric gases are compressed into a thinner layer, increasing the density and pressure at any given temperature. This compression affects the spectral lines formed in the atmosphere, causing them to broaden through a process called pressure broadening, where collisions between atoms perturb the energy levels and spread out the wavelengths of absorbed and emitted light. By measuring the width of spectral lines, astronomers can estimate a star's surface gravity, providing an independent check on the star's mass and radius derived from other methods. For Proxima Centauri, the spectral lines show significant pressure broadening, consistent with the calculated high surface gravity. The high gravity also affects the atmospheric scale height, the vertical distance over which atmospheric density decreases by a factor of E, about 2.7. On Earth, the atmospheric scale height is about 8 kilometers, meaning the atmosphere becomes noticeably thinner as you climb mountains or fly in airplanes. On Proxima Centauri, the scale height is only a few kilometers, meaning the transition from the dense photosphere to the thin corona occurs over a much shorter distance than in the Sun's atmosphere. Gravity also plays a crucial role in determining the escape velocity from Proxima Centauri's surface, the minimum speed an object must reach to escape the star's gravitational pull. Escape velocity is calculated as the square root of 2gm divided by r, where g is the gravitational constant, m is the star's mass, and r is its radius. For Proxima Centauri, this works out to about 270 kilometers per second, compared to about 618 kilometers per second for the Sun, and 11 kilometers per second for Earth. The lower escape velocity compared to the Sun reflects Proxima Centauri's lower mass, but it is still enormous by terrestrial standards, equivalent to about 1,000 times the speed of sound in air. This high escape velocity is crucial for understanding stellar winds and mass loss from red dwarfs. Some particles in the corona, heated to millions of degrees by magnetic activity, have speeds exceeding the escape velocity and flow away from the star as a stellar wind, similar to the solar wind that blows past Earth. For red dwarfs, the stellar wind is weaker than the solar wind because the star's lower luminosity and lower escape velocity mean fewer particles are heated to high enough speeds to escape. However, during major flares, energetic particles can be accelerated to extremely high velocities, allowing some material to escape even from a red dwarf's strong gravitational pull. The gravitational influence of Proxima Centauri extends far beyond its surface, shaping the orbits of any planets, asteroids, and comets in the system. Proxima Centauri b orbits at a distance of about 7 million kilometers, well within the star's gravitational dominance, completing an orbit every 11.2 days. The short orbital period is a direct consequence of Kepler's third law, which states that orbital period squared is proportional to orbital distance cubed divided by the star's mass. For a given orbital distance, lower stellar mass means longer orbital periods, but the habitable zone around Proxima Centauri is so close to the star that even with the reduced mass, the orbital period is just 11 days. This close orbit has important implications for the planet's rotation. Over time, tidal forces exerted by the star's gravity tend to synchronize a planet's rotation period with its orbital period, just as the moon's rotation is synchronized with its orbit around Earth, so that we always see the same face of the moon. If Proxima Centauri b is tidally locked, one side of the planet always faces the star and bakes under constant illumination, while the other side faces eternal darkness and freezes. This could create extreme temperature differences and unusual atmospheric circulation patterns, with heat transported from the day side to the night side by powerful winds. Gravitational interactions between Proxima Centauri and the Alpha Centauri binary pair also influence the star's long-term motion through space. While the three stars form a gravitationally bound system, Proxima orbits the binary pair at such a vast distance that the orbital period is hundreds of thousands of years, and the orbit may be quite eccentric, taking Proxima alternately closer to and farther from the binary stars. These long-period orbital variations could potentially perturb any comets or distant objects orbiting Proxima Centauri, occasionally sending them into the inner system where they might collide with planets. This process is similar to how the Oort cloud of comets surrounding our solar system is occasionally disturbed by passing stars or tidal forces from the galactic disk, sending comets into the inner solar system where they become visible as bright celestial apparitions. Understanding the gravitational dynamics of the Alpha Centauri system helps astronomers assess the stability of planetary orbits and the likelihood of impact events that could affect potential habitability of Proxima Centauri b. The rotation mystery. All stars rotate to some degree, spinning on their axes as they orbit through space, and rotation profoundly affects stellar structure and magnetic activity. Our Sun rotates once every 25 days at the equator and somewhat more slowly at higher latitudes, a differential rotation driven by the Sun's convective envelope. The Sun's rotation generates its magnetic field through a process called the solar dynamo, where convective motions and differential rotation twist and amplify magnetic fields in complex patterns that produce the 11-year sunspot cycle. Proxima Centauri also rotates, and determining its rotation period has been a long-standing challenge for astronomers because the star lacks the sunspot-like dark features that allow precise tracking of rotation on stars like the Sunday. Early estimates suggested a rotation period around 80 days, derived from long-term variations in the star's brightness that were attributed to dark spots rotating in and out of view. More recent studies, using improved photometry and spectroscopy, have refined this estimate to approximately 83 days, making Proxima Centauri a relatively slow rotator compared to some red dwarfs that spin as fast as once per day. The rotation period of a red dwarf strongly influences its magnetic activity level. Young red dwarfs spin rapidly because they form from collapsing clouds of gas that conserve angular momentum, causing rotation to speed up as the radius decreases, similar to how a figure skater spins faster when pulling in their arms. These rapidly rotating young red dwarfs have extremely powerful magnetic fields and intense flare activity because their fast rotation amplifies the dynamo mechanism generating the magnetic field. As red dwarfs age, they gradually spin down due to magnetic braking, a process where the star's magnetic field couples to its stellar wind, and the expanding wind carries away angular momentum, slowing the rotation. Over billions of years, a red dwarf's rotation period can increase from less than a day to hundreds of days, and its magnetic activity decreases correspondingly. Proxima Centauri's 83-day rotation period suggests it is an old star that has undergone substantial magnetic braking, yet it still exhibits significant flare activity, indicating that even slowly rotating red dwarfs maintain active magnetic dynamos. Measuring the rotation of Proxima Centauri requires indirect methods because the star is a point source, even in the largest telescopes, making direct imaging of surface features impossible. One method looks for periodic variations in the star's brightness caused by dark spots on the surface rotating in and out of view. As a dark spot rotates toward the Earth-facing hemisphere, the star appears slightly dimmer, then brightens as the spot rotates to the far side. By measuring these brightness variations over many rotation periods and constructing a light curve, astronomers can determine the rotation period. However, this method assumes that the dark spots are long-lived and maintain relatively fixed positions on the star's surface, which may not be true if the spots evolve rapidly or if the star's surface is covered with many spots that average out the brightness variations. Another method uses spectroscopy to measure the Doppler shift of spectral lines as different parts of the star's surface move toward or away from Earth due to rotation. The approaching side shows a blue shift, while the receding side shows a red shift, and the difference in wavelength depends on the rotation speed and the angle at which we view the star. This technique is called rotational broadening because it causes spectral lines to be broadened compared to a non-rotating star. The rotation of Proxima Centauri has important implications for the habitability of planets in the system. A star's rotation rate influences the geometry and strength of its magnetic field, which in turn affects the stellar wind and the space weather environment around the planets. Rapidly rotating stars tend to have strong, complex magnetic fields with many active regions, leading to frequent flares and intense stellar winds that can erode planetary atmospheres. Slowly rotating stars like Proxima Centauri have simpler magnetic fields, but they can still produce powerful flares if the magnetic field structure allows energy to build up before being released suddenly. The 83-day rotation period of Proxima Centauri means that any tidally locked planet, like Proxima Centauri b, would experience different magnetic orientations as the star rotates, potentially causing variable shielding from the stellar wind depending on the planetary magnetic field's orientation. If the planet has its own magnetic field, the interaction between the stellar and planetary magnetic fields would be complex and time variable, affecting how much atmosphere the planet loses over time. Understanding stellar rotation also provides clues to the star's formation history and age. Proxima Centauri's slow rotation suggests it is several billion years old enough to have lost most of its initial angular momentum through magnetic braking. However, determining the exact age of red dwarfs is notoriously difficult because they evolve so slowly that their properties change very little over billions of years. Unlike more massive stars that predictably exhaust their core hydrogen and evolve off the main sequence, allowing age determination from their evolutionary stage, red dwarfs remain on the main sequence for far longer than the current age of the universe. Astronomers must rely on indirect age indicators like rotation period, magnetic activity level, kinematics, and chemical composition. Proxima Centauri's space motion suggests it is part of the galactic thick disk population, stars that formed early in the galaxy's history when the disk was thicker and more dynamically heated than today. This kinematic evidence, combined with the slow rotation and low metallicity, suggests Proxima Centauri is likely at least a few billion years old, possibly as old as 6 to 10 billion years, making it older than the Sun by a couple of billion years and older than the Earth by more than 2 billion years. The distance factor. No discussion of Proxima Centauri's size would be complete without addressing its distance from Earth, because distance is fundamental to how we perceive and measure astronomical objects. Proxima Centauri lies approximately 4.24 light-years from our solar system, making it the closest known star beyond the Sun. To appreciate what this distance means, consider that a light-year is the distance light travels in 1 year, moving at the cosmic speed limit of about 300,000 kilometers per second, or about 1 billion kilometers per hour. Light from the Sun takes about 8 minutes to reach Earth, crossing the 150 million kilometers between us at this incredible speed. Light from Proxima Centauri takes 4.24 years to reach us, covering a distance of about 40 trillion kilometers, or roughly 268,000 times the Earth-Sun distance. This is the closest another star gets to us. and it illustrates the vast emptiness of interstellar space. The nearest stars are separated by distances millions of times their own diameters, like marbles scattered miles apart across an empty desert. The measurement of Proxima Centauri's distance has a fascinating history that parallels the development of astrometry, the precise measurement of stellar positions and motions. When Robert Innes discovered Proxima Centauri in 1915, he identified it as a possible companion to the Alpha Centauri system by observing that all three stars had similar proper motions, the apparent movement of stars across the sky due to their actual motion through space relative to the Sunday. Proper motion is measured in arcseconds per year, where an arcsecond is 1/3600th of a degree, an incredibly small angle equivalent to the size of a coin viewed from a distance of about 4 kilometers. Alpha Centauri has one of the largest proper motions of any bright star, about 3.7 arcseconds per year, meaning it drifts across the sky noticeably over decades or centuries. Proxima Centauri shares this large proper motion, confirming it is physically associated with Alpha Centauri and not just a chance alignment along our line of sight. Measuring the distance to Proxima Centauri precisely required parallax observations, where astronomers measure the star's apparent shift in position when viewed from opposite sides of Earth's orbit around the Sunday. The parallax angle, half the total angular shift, is inversely proportional to the distance, with closer stars showing larger parallax. Proxima Centauri's parallax is about 0.768 arcseconds, the largest parallax of any known star, confirming it as the closest stellar neighbor. Using the parallax, astronomers calculate the distance as 1 divided by the parallax in arcseconds, giving the distance in parsecs, where 1 parsec equals 3.26 light-years, or 31 trillion kilometers. Proxima Centauri's parallax of 0.768 arcseconds corresponds to a distance of about 1.3 parsecs, or 4.24 light-years. Modern parallax measurements from the Hipparcos and Gaia space missions have determined this distance with extraordinary precision, accurate to better than 1%, making Proxima Centauri one of the best measured stars in the sky. The proximity of Proxima Centauri makes it an invaluable laboratory for studying red dwarf stars in detail. At 4.24 light-years, the star is close enough that even modest telescopes can observe it, and large telescopes can conduct detailed spectroscopic and photometric studies that would be impossible for more distant red dwarfs. The discovery of Proxima Centauri b would have been much more difficult if the star were farther away, because the radial velocity amplitude induced by the planet decreases with distance, making the signal harder to detect against instrumental noise. The proximity also makes Proxima Centauri a prime target for future interstellar missions. Several proposed concepts for interstellar probes, including the Breakthrough Starshot initiative, envision sending small spacecraft to Proxima Centauri using laser propulsion to accelerate the probes to a significant fraction of light speed. Even at 20% the speed of light, the journey would take about 21 years, making Proxima Centauri the most achievable target for humanity's first interstellar voyage. Despite being the closest star, Proxima Centauri is invisible to the naked eye because its intrinsic faintness more than offsets its proximity. With an apparent visual magnitude of about 11, the star is roughly 1/16th the brightness of the faintest stars visible to the naked eye under perfect dark sky conditions. A telescope with at least a 4-inch diameter is required to see Proxima Centauri as a faint red speck near the much brighter Alpha Centauri binary. This invisibility highlights a crucial lesson about cosmic distances and stellar properties. Brightness alone does not indicate distance or size. The brightest star in the night sky, Sirius, is much more luminous than the Sun, but appears bright primarily because it is relatively nearby at 8.6 light-years. Other bright stars like Rigel and Deneb are intrinsically far more luminous than Sirius, luminous enough to be visible across thousands of light-years, but they appear less bright because of their great distances. Proxima Centauri represents the opposite case, close but faint, a tiny ember overshadowed by more luminous distant giants, yet holding secrets that could reshape our understanding of planets, life, and humanity's future among the stars. Comparing planetary systems, the discovery of Proxima Centauri b in 2016 transformed the star from an interesting but unremarkable nearby red dwarf into one of the most important targets in the search for life beyond Earth. Proxima Centauri b orbits within the star's habitable zone, the region where temperatures could allow liquid water to exist on a planet's surface, given the right atmospheric conditions. The planet has a minimum mass about 1.3 times Earth's mass, suggesting it could be a rocky world similar to Earth rather than a gas giant like Jupiter. Its orbital period of just 11.2 days means it orbits far closer to Proxima Centauri than Mercury orbits the Sun, at a distance of only about 7 million kilometers, or 5% the Earth-Sun distance. Despite this close orbit, the planet receives roughly the same amount of energy from its star as Earth receives from the Sun, because Proxima Centauri is so much fainter than the Sunday. This combination of Earth-like mass, rocky composition, and habitable zone orbit makes Proxima Centauri b one of the most intriguing exoplanets ever discovered, and a top priority for future observations aimed at detecting signs of life. Comparing the Proxima Centauri system to our solar system reveals striking differences that challenge our assumptions about planetary systems. In our solar system, the four inner rocky planets, Mercury, Venus, Earth, and Mars, orbit the Sun at distances ranging from 0.4 to 1.5 astronomical units. Where 1 AU equals the Earth-Sun distance, these planets take between 88 days for Mercury and 687 days for Mars to complete an orbit. The four outer gas giants, Jupiter, Saturn, Uranus, and Neptune, orbit at distances from 5 to 30 AU, with orbital periods ranging from 12 years for Jupiter to 165 years for Neptune. This architecture, with small, rocky planets near the star and giant planets farther out, is a consequence of how the solar system formed from a disk of gas and dust around the young Sunday. Rocky planets formed close to the Sun, where temperatures were high enough to vaporize volatile compounds like water and methane, leaving only refractory materials like silicates and iron. Giant planets formed farther out beyond the frost line where water ice could condense, providing enough solid material for cores massive enough to gravitationally capture hydrogen and helium gas. The Proxima Centauri system appears to be configured very differently. Proxima Centauri b orbits within the region that would correspond to Mercury's orbit, scaled to the lower luminosity of the red dwarf star. Evidence for additional planets in the system remains tentative, with some studies suggesting a possible second planet farther out and hints of additional signals in the radial velocity data, but no confirmed outer planets exist as of current knowledge. If Proxima Centauri lacks giant planets, this would suggest a different formation history compared to our solar system. One possibility is that the protoplanetary disk around Proxima Centauri contained less mass in gas and dust than the solar nebula, allowing only terrestrial planets to form. Another possibility is that the disk was dispersed more quickly by stellar winds or by encounters with other stars before giant planets could form. Red dwarf stars are thought to have longer-lived protoplanetary disks than more massive stars because their lower luminosity means radiation pressure disperses the disk more slowly, but other factors like stellar flares and magnetic activity could shorten the disk lifetime. The close orbit of Proxima Centauri b raises questions about how the planet formed and whether it migrated inward from a more distant orbit or formed in place. In the solar system, rocky planets are thought to have formed roughly at their current locations through the gradual accumulation of smaller bodies called planetesimals. However, forming planets close to a star is challenging because the strong tidal forces and high temperatures can prevent material from accumulating into larger bodies. One possibility is that Proxima Centauri b formed farther from the star where conditions were more favorable and then migrated inward through gravitational interactions with the protoplanetary disk or with other planets. This inward migration would have occurred early in the system's history, before the disk dissipated, bringing the planet to its current location within a few million years of formation. Alternatively, the planet might have formed in place if the protoplanetary disk was dense enough and cool enough at that distance for solid materials to accumulate. Understanding which scenario occurred requires detailed modeling of planet formation around red dwarf stars and could provide insights into whether habitable zone planets around red dwarfs are common or rare. The potential habitability of Proxima Centauri b depends on many factors beyond its orbital location in the habitable zone. One critical question is whether the planet retained or developed an atmosphere. Planets close to active stars like Proxima Centauri are bombarded by intense ultraviolet and X-ray radiation during frequent flares, and the stellar wind carries charged particles that can strip away atmospheric gases. If Proxima Centauri b formed with a substantial atmosphere and a protective magnetic field, it might have retained enough volatiles to maintain surface liquid water. If it lost its atmosphere early in its history, it could be a barren, rocky world like Mercury, baked by stellar radiation during flares and frozen during quiescent periods. Another factor is the planet's rotation. If Proxima Centauri b is tidally locked with one side permanently facing the star, the climate and habitability would be very different from Earth's. The day side could be too hot for liquid water, while the night side is too cold, with only a narrow ring-shaped region at the terminator between day and night potentially habitable. However, if the planet has a substantial atmosphere, winds could transport heat from the day side to the night side, moderating temperatures and potentially allowing liquid water to exist across both hemispheres. Determining the atmospheric properties of Proxima Centauri b is one of the highest priorities for exoplanet research and a key science goal for next-generation space telescopes. The spectral signature. The spectrum of a star is like a fingerprint containing detailed information about the star's temperature, composition, motion, and environment. When starlight is passed through a prism or diffraction grating, it spreads out into a rainbow of colors, from red through orange, yellow, green, blue, to violet, and extending into the invisible infrared and ultraviolet regions. Superimposed on this rainbow are thousands of dark lines called absorption lines, where specific wavelengths of light have been removed by atoms and molecules in the star's atmosphere. Each chemical element absorbs light at characteristic wavelengths determined by quantum mechanics, and by identifying which absorption lines appear in a star's spectrum, astronomers can determine which elements are present and in what quantities. Proxima Centauri's spectrum is rich in absorption features, including strong lines from hydrogen, helium, calcium, iron, and molecules like titanium oxide and water vapor. The pattern of these lines identifies the star as an M dwarf with a surface temperature around 3,000 degrees and confirms the presence of a cool outer atmosphere where molecules can exist without being dissociated by heat. The most prominent features in Proxima Centauri's visible light spectrum are the titanium oxide bands, broad swaths of absorption across multiple wavelengths created by the titanium oxide molecule. Titanium oxide is a particularly useful temperature indicator because it only exists in stellar atmospheres cooler than about 4,000 degrees. At higher temperatures, the molecule is broken apart into individual titanium and oxygen atoms. The strength of the titanium oxide absorption bands increases as temperature decreases, making them sensitive thermometers for cool stars. By comparing the observed titanium oxide band strengths in Proxima Centauri's spectrum to theoretical models and laboratory measurements, astronomers determine the star's surface temperature with an accuracy of about 100 degrees. Other molecular features in the spectrum include absorption from water vapor, carbon monoxide, and various metal hydrides, each providing additional constraints on temperature and chemical composition. The infrared spectrum, where Proxima Centauri emits most of its energy, shows additional molecular features not visible in the optical spectrum, including strong water vapor absorption that makes observing red dwarfs from the ground challenging because Earth's atmosphere also absorbs infrared light at many of the same wavelengths. Spectroscopy also reveals Proxima Centauri's motion through space by measuring the Doppler shift of spectral lines. When an object moves toward or away from us, the wavelengths of light it emits are shifted to shorter or longer wavelengths respectively, similar to how the pitch of a siren changes as an ambulance drives past. For Proxima Centauri, the spectral lines are shifted toward redder wavelengths, indicating the star is moving away from us at a velocity of about 22 kilometers per second. This velocity is the radial velocity, the component of the star's motion along our line of sight. Combined with the proper motion across the sky, the radial velocity gives the star's full three-dimensional velocity through space. Proxima Centauri's space motion shows it is traveling through the galaxy in a moderately elliptical orbit around the galactic center, typical of thick disk stars that formed early in the galaxy's history. The star's velocity and trajectory also allow astronomers to calculate when it will be closest to Earth, which occurred about 27,000 years ago when the star was slightly closer than it is now, at about 4.22 light-years. Over the next few tens of thousands of years, Proxima Centauri will gradually move farther from the Sun, and in several tens of thousands of years, another star, currently farther away, will take over as the closest stellar neighbor. One of the most scientifically valuable uses of Proxima Centauri's spectrum is searching for planets through the radial velocity method. When a planet orbits a star, both the planet and star orbit their common center of mass, causing the star to wobble slightly. This wobble creates periodic variations in the star's radial velocity as it alternately moves toward and away from us. By measuring these tiny velocity changes through the Doppler shift of spectral lines, astronomers can infer the presence of planets and determine their masses and orbital periods. The discovery of Proxima Centauri b was made using this technique, detecting a radial velocity variation of about 1.4 meters per second with an 11.2-day period. Measuring such small velocity changes requires extraordinarily precise spectrographs capable of tracking wavelength shifts of 1 part in 100 million, equivalent to detecting a shift smaller than the width of a single atom in a meter-long ruler. Instruments like HARPS, the High-Accuracy Radial Velocity Planet Searcher, achieve this precision by stabilizing the spectrograph in a temperature-controlled vacuum chamber and calibrating wavelengths using light from a stabilized laser frequency comb that provides reference lines with precisely known wavelengths. The spectrum of Proxima Centauri also contains information about the star's magnetic activity through emission lines, bright lines at specific wavelengths where atoms are emitting light rather than absorbing it. In inactive stars, emission lines are weak or absent because the atmosphere is relatively cool and atoms remain in their lowest energy states. In active stars like Proxima Centauri, magnetic activity heats portions of the atmosphere, and stellar flares can temporarily heat regions to tens of thousands of degrees. At these high temperatures, atoms become excited and emit light in characteristic lines, particularly the hydrogen alpha line in the red part of the spectrum and the calcium H and K lines in the blue-violet. By monitoring the strength of these emission lines over time, astronomers tracked the star's magnetic activity level and flare frequency. Long-term monitoring shows that Proxima Centauri's emission line strength varies somewhat over weeks to months, possibly indicating changes in the number or distribution of active regions on the stellar surface, though the variations do not show a clear periodic pattern like the Sun's 11-year activity cycle. Understanding these activity variations is important for assessing the radiation environment experienced by planets and for predicting when major flares are likely to occur. The age question. Determining the age of Proxima Centauri is one of the most challenging problems in stellar astrophysics because red dwarf stars evolve so slowly that they change very little over billions of years. More massive stars like the Sun have well-defined evolutionary tracks where they predictably exhaust core hydrogen, expand into giants, and eventually shed their envelopes, allowing astronomers to determine ages by comparing observed properties to evolutionary models. A Sun-like star's age can be estimated to within about 10 to 20% by measuring its luminosity, temperature, and composition and comparing to stellar models. Red dwarfs like Proxima Centauri remain on the main sequence, stably fusing hydrogen for timescales far longer than the current age of the universe, making age determination from evolutionary state impossible. Instead, astronomers must rely on indirect age indicators that correlate with age but have larger uncertainties. These include the star's rotation period, magnetic activity level, kinematics, chemical composition, and membership in stellar populations with known ages. Proxima Centauri's rotation period of 83 days suggests an old age because red dwarfs spin down over time due to magnetic braking. Young red dwarfs with ages less than 100 million years typically rotate with periods of a few days or less and show extremely high magnetic activity. As the star ages, the rotation period gradually increases and magnetic activity decreases. By comparing Proxima Centauri's rotation period to theoretical models of rotational evolution and to observations of red dwarfs in star clusters with known ages, astronomers estimate the star's age at somewhere between 4 and 7 billion years, comparable to or somewhat older than the Sun's age of 4.6 billion years. However, this estimate has significant uncertainty because the rate of magnetic braking depends on the star's mass, magnetic field strength, and stellar wind properties, all of which vary between stars and are not perfectly understood. Some red dwarfs spin down faster than models predict, while others spin down more slowly, introducing scatter in the rotation period versus age relationship. The chemical composition of Proxima Centauri provides another age clue. The star's metallicity, the abundance of elements heavier than hydrogen and helium, is about 85% that of the Sun, indicating it formed from gas that had been slightly less enriched with heavy elements by previous generations of stars. In general, older stars in the galaxy have lower metallicities because they formed earlier when less stellar nucleosynthesis had occurred, while younger stars have higher metallicities because they incorporate material from more previous stellar generations. However, the relationship between age and metallicity has considerable scatter because the chemical enrichment history of the galaxy is complex, with different regions of the galaxy enriching at different rates. The metallicity of 85% solar is consistent with ages ranging from 4 to 10 billion years, not providing a tight constraint. More detailed chemical analysis looking at the ratios of specific elements like magnesium to iron or aluminum to iron can provide better age constraints because these ratios change in characteristic ways as the galaxy ages. But such detailed abundance measurements for Proxima Centauri are challenging due to the star's faintness and crowded spectrum. The kinematics of Proxima Centauri, its motion through the galaxy, suggest it belongs to the thick disk population, stars that formed early in the galaxy's history when the disk was thicker and more dynamically heated than today. Thick disk stars typically have ages between 8 and 12 billion years older than the thin disk population to which the Sun belongs. However, the boundary between thick disk and thin disk populations is not sharp, and some stars with thick disk kinematics may actually be old, thin disk stars whose orbits were perturbed by gravitational interactions or spiral arm passages. The space velocity of Proxima Centauri is moderately high compared to the local standard of rest, the average motion of stars in the Sun's neighborhood, which is consistent with either an old, thick disk star or an old, thin disk star. Recent studies combining all available age indicators suggest that Proxima Centauri is likely between 5 and 8 billion years old, making it older than Earth and possibly formed before our solar system came into existence. But the uncertainty remains about plus or minus 2 billion years. The age of Proxima Centauri has important implications for the potential habitability of Proxima Centauri b. If the star is 5 to 8 billion years old, the planetary system has existed long enough for complex life to evolve, assuming the planet maintained habitable conditions. Earth formed about 4.6 billion years ago, and complex multicellular life arose about 600 million years ago, suggesting that billions of years may be required for intelligence to evolve. If Proxima Centauri b formed with its star and maintained a stable environment with liquid water and a protective atmosphere, it has had sufficient time for life to emerge and possibly develop complexity. However, red dwarf stars remain highly magnetically active for much longer than Sun-like stars, with flare activity persisting for billions of years. If Proxima Centauri b has been subjected to intense flare bombardment throughout its history, maintaining a habitable environment might be very difficult, and the emergence of life might be unlikely or delayed. Resolving the age question and understanding the star's magnetic activity history over billions of years are crucial for assessing the potential for life in the system. The habitable zone. The concept of the habitable zone, sometimes called the Goldilocks zone, refers to the range of distances from a star where a planet with a suitable atmosphere could maintain liquid water on its surface. Liquid water is considered essential for life as we know it because water is an excellent solvent for biochemical reactions and remains liquid over a wide temperature range. The inner edge of the habitable zone is defined by the runaway greenhouse effect, where stellar heating causes all surface water to evaporate into the atmosphere as water vapor, which is a powerful greenhouse gas that traps even more heat, leading to a feedback loop that boils away the oceans and creates a Venus-like hell world. The outer edge of the habitable zone is defined by the maximum greenhouse effect, where even an atmosphere composed entirely of carbon dioxide cannot trap enough heat to prevent surface water from freezing. For our Sun, the habitable zone extends from about 0.9 AU to about 1.7 AU, placing Earth comfortably near the inner edge and Mars just beyond the outer edge. For Proxima Centauri, with its much lower luminosity of only 0.17%, the Sun's luminosity, the habitable zone is located much closer to the star, extending from roughly 0.04 to 0.09 AU, or about 4 to 9 million kilometers from the star. Proxima Centauri b orbits at approximately 0.048 AU, or 7 million kilometers, placing it squarely within the habitable zone. However, being in the habitable zone does not guarantee habitability, because many other factors affect whether a planet can maintain liquid water. One critical factor is atmospheric composition. A thick carbon dioxide atmosphere can create a strong greenhouse effect that keeps a planet warm enough for liquid water even at the outer edge of the habitable zone, while a thin atmosphere provides little greenhouse warming, and the planet might be too cold even at the inner edge. Earth's atmosphere, with its modest carbon dioxide content and significant nitrogen and oxygen, provides just enough greenhouse effect to keep the average surface temperature above freezing. Venus, closer to the Sun and with a thick carbon dioxide atmosphere, experiences a runaway greenhouse effect, with surface temperatures hot enough to melt lead. Another crucial factor for habitability is the planet's mass and composition, because these determine whether the planet can retain an atmosphere against atmospheric escape processes. Low-mass planets with weak gravity have low escape velocities, making it easier for atmospheric molecules to gain enough thermal energy to escape to space. High-energy radiation from stellar flares can dissociate water molecules into hydrogen and oxygen, and the light hydrogen can easily escape from low-mass planets, gradually depleting water over time. Proxima Centauri B's mass of at least 1.3 Earth masses suggests it has sufficient gravity to retain an atmosphere over billions of years, assuming it formed with volatiles and has not been stripped by the intense stellar activity. The planet's composition is uncertain because radial velocity measurements only provide a minimum mass and no information about radius or density. If the planet has a rocky composition similar to Earth, its radius would be roughly 1.1 Earth radii, giving a density comparable to Earth's and suggesting a solid surface on which liquid water could pool. If the planet has a significant envelope of hydrogen and helium gas, it could be more like a mini Neptune without a solid surface and potentially uninhabitable despite being in the habitable zone. The close orbit required to be in Proxima Centauri's habitable zone creates several challenges for habitability beyond just atmospheric retention. One challenge is tidal locking. When a planet orbits close to its star, tidal forces cause the planet's rotation to slow down until the same hemisphere always faces the star, just as the Moon is tidally locked to Earth. For Proxima Centauri b, with its 11-day orbital period, tidal locking probably occurred within the first few million years after formation. A tidally locked planet has one side in perpetual daylight and the other in perpetual darkness, creating extreme temperature differences unless the atmosphere is thick enough to redistribute heat through global wind circulation. Climate models suggest that if Proxima Centauri b has an atmosphere with pressure comparable to Earth's, winds would transport enough heat from the day side to the night side to prevent the atmosphere from freezing out on the night side and creating a permanent ice cap. However, if the atmosphere is too thin, it might collapse onto the night side as ice, leaving the day side exposed to harsh stellar radiation. Despite these challenges, some researchers argue that planets in red dwarf habitable zones might actually be more likely to develop and maintain life than Earth-like planets around Sun-like stars. Red dwarfs live for trillions of years, compared to the Sun's 10 billion-year lifetime, providing vastly longer timescales for life to emerge and evolve. If a planet around a red dwarf can maintain habitable conditions despite the close orbit and stellar activity, it would have hundreds of billions or even trillions of years for biological complexity to develop, potentially allowing evolution to explore far more possibilities than possible in the relatively brief, habitable lifetime of Earth-like planets around Sun-like stars. Additionally, red dwarfs are the most common stars in the galaxy, outnumbering Sun-like stars by about 10 to 1. If even a small fraction of red dwarfs host habitable planets, they could represent the majority of habitable real estate in the galaxy, making red dwarf systems the most likely places to find life rather than Sun-like systems. Testing these ideas requires detecting and characterizing the atmospheres of planets like Proxima Centauri b, a challenge that astronomers are working to meet with next-generation telescopes and instruments. The magnetic dynamo. The intense magnetic activity of Proxima Centauri is one of its most remarkable features and is intimately connected to the star's internal structure. Magnetic fields in stars are generated by the dynamo mechanism, where convective motions of electrically conducting plasma create electric currents that produce magnetic fields. In our Sun, the dynamo operates primarily at the interface between the radiative core and the convective envelope, creating the sunspot cycle and driving solar activity. Red dwarfs like Proxima Centauri, being fully convective throughout their interiors, generate magnetic fields through a different type of dynamo that operates throughout the entire star. The vigorous convective churning continuously stretches and twists magnetic field lines, amplifying the field and creating complex structures that emerge through the photosphere into the corona. The fully convective dynamo is less well understood than the interface dynamo operating in Sun-like stars because the physics is more complex and observations of red dwarf magnetic fields are challenging. The magnetic field of Proxima Centauri has been measured through several techniques that provide complementary information. One method is Zeeman spectroscopy, which measures the splitting of spectral lines in the presence of a magnetic field. When atoms absorb or emit light in a magnetic field, the spectral lines split into multiple components with slightly different wavelengths, and the amount of splitting depends on the magnetic field strength. By analyzing the detailed shapes of spectral lines, astronomers can infer the strength and geometry of the surface magnetic field. Measurements suggest that Proxima Centauri has a surface magnetic field of several hundred Gauss, comparable to the strongest sunspot fields on the Sun, but covering a much larger fraction of the stellar surface. For comparison, Earth's magnetic field is about half a Gauss, and the Sun's average surface field away from sunspots is about 1 Gauss, showing that Proxima Centauri is an extremely magnetic object. Another technique for studying red dwarf magnetic fields is monitoring their radio emission. Magnetic activity accelerates electrons to high velocities, and these energetic electrons spiraling around magnetic field lines emit radio waves through a process called synchrotron radiation. Observations of Proxima Centauri at radio wavelengths detect both steady emission and transient bursts associated with flares, confirming the presence of strong magnetic fields and accelerated particles in the corona. The radio emission varies over timescales of hours to days, suggesting that the magnetic field structure is dynamic and evolving as convective motions at the surface twist and reconfigure the field. Long-term radio monitoring combined with simultaneous optical observations provides insights into how magnetic energy builds up before flares and how the magnetic field recovers after energy release. Understanding this cycle is important for predicting flare occurrence and assessing the radiation environment around the star. The strength and topology of Proxima Centauri's magnetic field have important consequences for any planets in the system. The stellar magnetic field extends into the surrounding space, creating a stellar magnetosphere analogous to Earth's magnetosphere that shields us from cosmic rays. However, the stellar magnetosphere also channels the stellar wind, streams of charged particles flowing from the star's corona. For Proxima Centauri b orbiting close to the star, the interaction between the stellar magnetosphere and any planetary magnetic field would be intense and complex. If the planet has a strong magnetic field, it could create a protective bubble that deflects the stellar wind and reduces atmospheric erosion. If the planet lacks a magnetic field, the stellar wind would directly impact the upper atmosphere, gradually stripping away atmospheric gases over millions to billions of years. Earth's magnetic field is crucial for maintaining our atmosphere against the solar wind, and the same would likely be true for Proxima Centauri b, though the much stronger stellar activity makes the challenge more severe. Recent theoretical work suggests that fully convective red dwarfs like Proxima Centauri might generate magnetic fields through a mechanism called a small-scale turbulent dynamo, in addition to the large-scale dynamo that creates long-lived active regions. The turbulent dynamo operates on small spatial scales within convective cells, creating numerous small magnetic flux tubes that emerge randomly across the stellar surface rather than being concentrated in active regions like sunspots. This could explain why Proxima Centauri shows persistent magnetic activity even with its relatively slow rotation, which would produce only weak large-scale field in traditional dynamo theories. The small-scale dynamo continuously generates magnetic field regardless of rotation rate, maintaining activity over the star's entire lifetime. Testing these theoretical predictions requires detailed observations of red dwarf surface features using techniques like Doppler imaging, where spectral line profiles are analyzed to reconstruct images of the stellar surface, showing the distribution of dark spots and bright regions. Such observations are challenging for faint red dwarfs, but are becoming feasible with the largest telescopes and most advanced instruments. The life expectancy. One of the most extraordinary features of Proxima Centauri is its lifespan. While massive hot stars burn through their nuclear fuel in only a few million years, and sun-like stars last about 10 billion years, red dwarfs, like Proxima Centauri, will shine for trillions of years, far longer than the current age of the universe. This remarkable longevity arises from the combination of low mass, complete convective mixing, and slow fusion rates. Proxima Centauri's mass is only about 12% the Sun's mass, and the rate at which stars fuse hydrogen depends very strongly on mass. Higher mass stars have hotter, denser cores where fusion proceeds rapidly, generating enormous luminosity but exhausting fuel quickly. Lower mass stars have cooler cores where fusion proceeds slowly, generating modest luminosity and consuming fuel at a leisurely pace. The mass-luminosity relationship for main sequence stars shows that luminosity is approximately proportional to mass raised to the power of 3.5, meaning a star with twice the Sun's mass is about 11 times more luminous, while a star with half the Sun's mass is only about 1/11th as luminous. For Proxima Centauri, with 12% the Sun's mass, the theoretical luminosity based on the mass-luminosity relationship would be approximately 0.2% the Sun's luminosity, close to the observed value of 0.17%. The lifetime of a star is approximately proportional to its mass divided by its luminosity, because the mass determines how much fuel is available, while the luminosity determines how quickly that fuel is consumed. For the Sun, with one solar mass and one solar luminosity, the lifetime is about 10 billion years. For Proxima Centauri, with 0.12 solar masses and 0.0017 solar luminosities, the lifetime would be about 0.12 divided by 0.0017, or roughly 70 times the Sun's lifetime, about 700 billion years. However, this calculation assumes only the core hydrogen is fused. As in the Sunday, Proxima Centauri's complete convective mixing means all the hydrogen throughout the star will eventually be fused, extending the lifetime by another factor of several times. Detailed evolutionary models, taking this into account, predict that Proxima Centauri will remain on the main sequence, stably fusing hydrogen for approximately 4 trillion years. To put this timescale in perspective, consider that the universe is currently about 13.8 billion years old, meaning Proxima Centauri is only about 0.3% through its main sequence lifetime if it formed near the beginning of the universe. Even if it formed much more recently, say 6 billion years ago, it has used less than 1/10 of 1% of its available fuel. The star will continue shining essentially unchanged for thousands of times longer than the universe has existed so far. By the time Proxima Centauri exhausts its hydrogen fuel, the universe will be unrecognizably different from today. All sun-like stars will have evolved into white dwarfs or neutron stars. Galaxies will have merged into a few enormous elliptical galaxies. Star formation will have largely ceased as available gas is consumed or ejected, and the universe will be dominated by slowly cooling stellar remnants and black holes. Proxima Centauri and other red dwarfs will be among the last objects in the universe still generating energy through nuclear fusion. Tiny beacons in an increasingly dark and empty cosmos. The extraordinary longevity of red dwarfs has profound implications for the potential evolution of life and civilizations. If Proxima Centauri b or other planets around red dwarfs can maintain habitable conditions, life would have timescales vastly longer than available on Earth to evolve and develop complexity. Earth has been habitable for perhaps 4 billion years and will remain habitable for perhaps another 1 to 2 billion years before the Sun's increasing luminosity triggers a runaway greenhouse effect and boils away the oceans. In total, Earth's habitable lifetime is roughly 5 billion years. A planet around Proxima Centauri could potentially remain habitable for trillions of years, hundreds or thousands of times longer, if atmospheric erosion and stellar activity do not render it uninhabitable earlier. This extended timescale might allow biological evolution to explore possibilities that would never occur in the shorter lifetimes of planets around sun-like stars, potentially leading to forms of life and intelligence vastly different from anything we can imagine. The eventual fate of Proxima Centauri, after it exhausts its hydrogen fuel, is uncertain because no red dwarf has ever reached this stage in the history of the universe. Theoretical models predict that when the hydrogen is finally gone, the star will contract and heat, beginning to fuse helium into carbon and oxygen in its core. However, the helium fusion stage will be brief and unstable, lasting perhaps only a few 100 billion years, and the star will not have enough mass to ignite carbon fusion. The core will become a carbon-oxygen white dwarf, supported by electron degeneracy pressure, while the outer layers gradually drift away over timescales of hundreds of billions of years. The end result will be a white dwarf with roughly the mass of Proxima Centauri, but a radius only about 1% the current radius, roughly the size of Earth. This white dwarf will slowly cool and fade over trillions of years, eventually becoming a black dwarf, a cold, dark stellar remnant that no longer emits significant light. The time required for a white dwarf to cool to the temperature of the cosmic background radiation is estimated at hundreds of trillions to quadrillions of years, longer than any timescale we can meaningfully contemplate. The size in context. After exploring Proxima Centauri from multiple perspectives, we can now return to the question posed at the beginning of this documentary. How big is Proxima Centauri really? The answer depends on what aspect of size we are considering. In terms of radius, Proxima Centauri is small, only about 14% the Sun's radius, or roughly 1.2 times Jupiter's radius, making it barely larger than the biggest planet in our solar system. You could line up about 7 Proxima Centauri stars side by side across the diameter of the Sun, and you could fit roughly 280 Proxima Centauri stars inside the Sun's volume. Yet this small size conceals an object of extraordinary density and mass. Proxima Centauri contains 12% the Sun's mass, about 123 times Jupiter's mass, compressed into that small volume, giving it an average density about 40 times that of Jupiter and roughly 55 times the density of water. The star's interior is a dense plasma where atoms are stripped of electrons and temperatures reach 15 million degrees, conditions so extreme that nuclear fusion transforms hydrogen into helium and releases the energy that makes the star shine. In terms of luminosity and energy output, Proxima Centauri is tiny compared to the Sun, emitting only about 1/6 as much energy per second. This faint output makes the star invisible to the naked eye despite being the closest stellar neighbor, and it confines the habitable zone to a narrow ring very close to the star, where any planets must endure the full force of intense stellar flares and magnetic activity. Yet this low luminosity is precisely what allows Proxima Centauri to shine for trillions of years, far outlasting more luminous stars that burn bright but die young. In terms of influence and significance, Proxima Centauri is enormous. As the nearest star to our solar system, it is the most accessible target for future interstellar missions and the first place humanity might search for signs of life beyond Earth. The discovery of Proxima Centauri b transformed the star from an astronomical curiosity into one of the most important objects in the sky, a potential harbor for life, orbiting right on our cosmic doorstep. Perhaps the most important lesson from studying Proxima Centauri is that size in astronomy is not a simple concept. A star can be physically small, yet incredibly massive, faint invisible light, yet incredibly energetic at other wavelengths, tiny compared to giant stars, yet large compared to planets, and seemingly insignificant, yet profoundly important for understanding stellar physics and planetary habitability. Proxima Centauri challenges our intuitions about what makes something big or small, forcing us to consider multiple dimensions of size simultaneously. It reminds us that the universe is filled with objects that defy simple categorization and that understanding cosmic phenomena requires looking beyond surface appearances to grasp the underlying physical principles. The star also exemplifies the diversity of stellar types and behaviors, representing the most common class of stars, yet possessing unique properties that continue to surprise and challenge astronomers. The study of Proxima Centauri has also revealed how far astronomical techniques have advanced over the past century. When the star was discovered in 1915, astronomers could measure only its position, motion, and approximate brightness. Today, we can measure its mass, radius, temperature, chemical composition, rotation period, magnetic field strength, flare frequency, and even detect planets orbiting it from 40 trillion kilometers away. We have constructed detailed theoretical models of its interior structure, predicted its future evolution over trillions of years, and assessed the potential habitability of its planetary system. This progress reflects decades of technological innovation in telescopes, detectors, spectrographs, and computational methods, combined with fundamental advances in our understanding of physics, from quantum mechanics to general relativity. The story of Proxima Centauri is also the story of how humanity has learned to comprehend the universe through observation, measurement, and reason. Looking forward, Proxima Centauri will continue to be a primary target for astronomical research for decades to come. Upcoming missions like the James Webb Space Telescope and future extremely large ground-based telescopes will observe Proxima Centauri b in detail, searching for atmospheric gases that might indicate habitable conditions or even biosignatures that could reveal the presence of life. Dedicated monitoring campaigns will continue tracking the star's flare activity and magnetic behavior, building a long-term database that will help us understand the evolution of red dwarf activity and assess habitability. Theoretical studies will continue refining our models of red dwarf interiors, convection, and magnetic dynamos, striving to understand why these stars behave as they do. And in the more distant future, perhaps within the next century, humanity might launch probes toward Proxima Centauri, sending tiny spacecraft accelerated to a fraction of light speed that could reach the system within a few decades and send back close-up images and data from the nearest star beyond the Sun, finally revealing whether Proxima Centauri b is a barren rock, a water world, or perhaps even a living planet. A tiny giant. Our journey to understand how big Proxima Centauri really is has taken us from the star's discovery in the early 20th century through the development of stellar physics, the measurement of stellar properties, and the implications for planets and life. We have seen that Proxima Centauri is simultaneously tiny and enormous depending on how we measure it. With a radius only slightly larger than Jupiter and a luminosity less than 1% the Sun's, it seems insignificant, a faint red ember barely qualifying as a star. Yet with a mass 12% the Sun's and an interior density dozens of times that of Earth's rocks, compressed by gravity to conditions where nuclear fusion transforms matter and energy, according to Einstein's equation, it is a cosmic powerhouse that will outlive the Sun by hundreds of times and perhaps harbor worlds where life could evolve over timescales unimaginable around more massive stars. The story of Proxima Centauri reminds us that the cosmos operates on scales and timescales that transcend human experience. A star that is small by astronomical standards is still incomprehensibly large and energetic compared to anything in our everyday lives. Containing more than 40,000 Earth masses in a sphere you could fit inside the Sun's orbit of Mercury. The nearest star beyond the Sun is so far away that light from it takes more than 4 years to reach us, traveling at the cosmic speed limit across 40 trillion kilometers of empty space. The star will shine essentially unchanged for thousands of times longer than our entire species has existed, for longer than complex life has existed on Earth, for longer than our planet has existed, indeed, for longer than the universe has existed so far in its current form. These scales challenge our intuitions and force us to expand our conception of what is possible. Proxima Centauri also stands as a testament to human curiosity and ingenuity. A century ago, no one knew this star existed. Today, we know its mass, radius, temperature, age, rotation period, chemical composition, magnetic field strength, and even that it hosts planets where life might exist. We achieve this understanding not through magic or divine revelation, but through patient observation, careful measurement, mathematical reasoning, and the development of theories grounded in testable predictions. Every property of Proxima Centauri we discussed in this documentary was measured or calculated by people using instruments and methods we understand, following physical laws that we have tested countless times. This knowledge is not perfect or complete, and many questions remain unanswered, but it is real and reliable, built on foundations of evidence and logic that anyone can examine and verify. The study of Proxima Centauri also illustrates how scientific understanding evolves over time. Early estimates of the star's properties were rough approximations based on limited data. As better telescopes and instruments became available and theoretical understanding improved, the estimates became more refined and accurate. Some properties, like the parallax and distance, are now known with extraordinary precision, while others, like the exact age and magnetic field topology, remain uncertain. This is how science works. Not claiming absolute truth, but progressively approaching better approximations through cycles of observation, theory, prediction, and testing. The uncertainties we acknowledge today are not signs of weakness, but of honesty and intellectual rigor, recognizing the limits of current knowledge while working to push those limits farther. Perhaps most importantly, the study of Proxima Centauri reveals our place in the universe. We live on a planet orbiting a medium-sized star in the outskirts of a galaxy containing hundreds of billions of stars, most of which are smaller and fainter than our Sun, more similar to Proxima Centauri than to the Sunday. If our Sun is typical of stars supporting complex life, then most stars in the galaxy are too small and cool. But if red dwarfs like Proxima Centauri can support habitable planets despite their intense magnetic activity, then most stars in the galaxy might host habitable worlds, and life could be far more common than we ever imagined. The discovery of Proxima Centauri b opened this possibility, showing that even the smallest stars can have planets in their habitable zones, and forcing us to reconsider our assumptions about where life might arise. As we conclude this exploration, we return to the image of Proxima Centauri as seen in our telescopes, a faint red point of light invisible to the naked eye, yet holding within it the same fundamental physics that governs all stars, the same processes of fusion that power the sun and illuminate our world. This tiny star, barely larger than a planet, yet impossibly dense and hot, represents both the extraordinary diversity of the cosmos and the underlying unity of physical law. It burns with the same nuclear fire that powered the stars that forged the carbon, oxygen, and iron in our bodies. It obeys the same laws of gravity and thermodynamics that keep Earth in orbit and our hearts beating. It evolves according to the same principles of stellar structure that will one day cause our sun to expand into a red giant and eventually fade into a white dwarf. Proxima Centauri is both utterly alien, a world of superhot plasma and nuclear transmutation, and fundamentally familiar, made of the same matter and energy that compose everything we know. How big is Proxima Centauri really? The answer is that it is exactly the size it needs to be to exist as a stable hydrogen-fusing star with 12% the Sun's mass, shaped by the laws of physics into a configuration that balances gravitational collapse against fusion pressure, producing a radius 14% the Sun's and a luminosity less than 1% the Sun's, shining steadily for trillions of years while emitting most of its energy as infrared light we cannot see with our eyes. It is small enough to challenge our ability to measure it and large enough to contain 40,000 Earth masses. It is close enough to study in detail and far enough that light from it takes over 4 years to reach us. It is faint enough to be invisible without a telescope and energetic enough to potentially sterilize planets with its flares. It is common enough that most stars in the galaxy are similar objects, and unique enough that it is the only star at its particular distance and configuration. It is the perfect size to be Proxima Centauri, our nearest stellar neighbor, and a window into understanding the smallest stars that will be the last lights burning in the universe's distant future, when everything else has faded into darkness and these tiny red embers are the only remaining memory of the age of stars.